and Environment Engineering. NIT Rourkela Engineering. Achievements of the department include Center of Excellence in Tissue Engineering and Orthopedic Tissue Engineering and Rehabilitation, DBT Program Support in Tissue Engineering, Program Support in Bioinformatics, DSF, FIST Level 1. Bioprocess Engineering. Biomaterials and Tissue Engineering. Medical Electronics and Instrumentation.
Come to a point which is close to one of the
The department also has an
But
active
do you have to do the simulation, the whole simulation, and then only you can interact?
Society of Student Activity Center NIT Rourkela. The club conducts several activities around the year. The department also organized a biotechnology popularization and skill development program 2020 from January 24 to 25, 2020. Sponsored by Biotech Research Society India (BRSI) in association with Genesis Club. The program aims to motivate the students to pursue a career in biotechnology. The institute offers a total of 60 seats, 30 for each stream, for the undergraduates under the BTech program through Joint Seat Allocation Authority, direct admission of students abroad, Indian Council for Cultural Relations, and Ministry of External Affairs. Apart from BTech programs, the department also offers MTech 2 years and PhD programs to the graduates. Department of Biotechnology and Medical Engineering of National Institute of Technology, Rourkela, was established in the year 2007 with the future goal of producing quality engineers by offering multidisciplinary teaching and research, developing world-class resources, and in making outstanding contributions in the realm of biomedical and biotechnology, a goal it has been achieving at a rapid rate. The department is divided into two streams, biotechnology and biomedical. There are 6 academics and research groups. Currently, a category of faculty members from diverse fields have been appointed for carrying forth the department. The department is MBA accredited. We have various state-of-the-art labs too. Cell and molecular engineering. Achievements of the department include Center of Excellence in Tissue Engineering and Orthopedic Tissue Engineering and Rehabilitation, DBT Program Support in Tissue Engineering, Program Support in Bioinformatics, DSF FIST Level 1.
Grown in a carbon dioxide incubator. This is a protocol for preparation of the pancreatitis nodal nanoparticles, which was prepared by the nanoprecipitation method.
The critical reason on femur bone extend from
Bioprocess Engineering. Agricultural and Environment Engineering. Biomechanics and Biochemistry. Biomaterials and Tissue Engineering. Medical electronics and instrumentation. The department also has been technical side, Genesis, registered under the Technical Society of Student Activity Center in NIT Rourkela. The club conducts several activities around the year. The department also organizes a participative popularization and skill development program. The program aims to motivate the school children to pursue a career to inspire research. Numerous activities such as seed plantation, vermi compost production, sanitation, health camp, sustainable agricultural practices have been performed in some of the nearby villages by the women organization of NIT Rourkela. The institute offers a total of 60 seats, 30 for each stream for the undergraduate under the BTech program through joint seat allocation ability, direct admission of students abroad, Indian Council for Cultural Relations, and Ministry of External Affairs. To join BTech programs, the department of Biotechnology and Chemical Engineering of National Institute of Technology, Rourkela, was established in the year 2007 with the business goal of developing quality engineers by offering multidisciplinary teaching and research, developing world-class resources, and in making outstanding contributions in the realm of biomedical and biotechnology. A goal it has been achieving at a rapid rate. The department is divided into two streams, biotechnology and biomedical. There are 6 academic and research groups. Currently, a category of faculty members from diverse fields have been appointed for carrying forth the department. The department is FDA accredited. We have various state-of-the-art labs too. Cell and molecular engineering, achievements of the department include Center of Excellence in Tissue Engineering and Orthopedic Tissue Engineering and Rehabilitation, DBT Program Support in Tissue Engineering, Program Support in Bioinformatics, DSF, TIS, Level 1. Bioprocess Engineering, Agricultural and Environment Engineering, Biomechanics and Biotransfer, Biomaterials and Tissue Engineering, Medical Electronics and Instrumentation, the department also has an active technical class, Genesis, registered under the Technical Society of Student Activity Center in NIT Rourkela. The club conducts several activities around the year. The department also organized a biotechnology popularization and skill development program. The program aims to motivate the school children to pursue a career in biotechnology. Various activities such as seed plantation, vermicompost production, sanitation, healthcare, sustainable agricultural practices, have been performed in some of the nearby villages by the NIT Rourkela BM of NIT Rourkela. The institute offers a total of 60 seats, 34 each stream, for the undergraduates under the BTech program through joint seat allocation authority, direct admission of students abroad, Indian Council for Cultural Relations, and Ministry of External Affairs. Apart from BTech programs, the department also offers MTech 2 years and PhD programs to the graduates. Department of Biotechnology and Medical Engineering of National Institute of Technology, Rourkela, was established in the year 2007 with the future goal of producing quality engineers by offering multidisciplinary teaching and research, developing world-class resources, and in making outstanding contributions in the realm of biomedical and biotechnology. A goal it has been achieving at a rapid rate. The department is divided into two streams, biotechnology and biomedicine. There are 6 academic and research streams. Currently, a cadre of faculty members from diverse fields have been appointed for carrying forward the department. The department is MBA accredited. We have various state-of-the-art labs too. Cell and molecular engineering, achievements of the department include Center of Excellence in Tissue Engineering and Orthopedic Tissue Engineering and Rehabilitation, DBT Program Support in Tissue Engineering, Program Support in Bioinformatics, DSF, FIST, Level 1. Bioprocess Engineering, Agricultural and Environment Engineering, Biomechanics and Biotransfer, Biomaterials and Tissue Engineering, Medical Electronics and Instrumentation, The department also has an active technical club, Genesis, registered under the Technical Society of Student Activity Center in NIT Rourkela. The club conducts several activities around the year. The program is to motivate school children to pursue this area through various activities such as seed plantation, learning compost production, sanitation, health camp, sustainable agricultural practices have been performed in some of the nearby villages by the Unnat Bharat Abhiyan of NIT Rourkela. The institute offers a total of 60 seats, 30 for each stream for the undergraduate under the BTech program through joint seat allocation ability, direct admission to students abroad, Indian Council for Cultural Relations, and Ministry of External Affairs. Apart from BTech programs, the department also offers MTech, 2 years, and PhD programs for the graduates. Department of Biotechnology and Biomedical Engineering of National Institute of Technology, Rourkela, was established in the year 2007 with the future goal of producing quality engineers by offering multidisciplinary teaching and research, developing world-class resources, and in making outstanding contributions in the realm of biomedical and biotechnology. We go, it has been achieving at a rapid rate. The department is divided into 2 streams, biotechnology and biomedical. There are 6 academic and research streams. Currently, a cadre of 18 faculty members from diverse fields have been appointed for carrying forth the department. The department is FDA accredited. We have various state-of-the-art labs too. Biomechanics and biotransfer. Agricultural and environment engineering. Civil and roadmap engineering. Achievements of the department include Center of Excellence in Tissue Engineering and Orthopedic Tissue Engineering and Rehabilitation, DBT Program Support in Tissue Engineering, Program Support in Bioinformatics, DSM, FIST, Level 1. Biomaterials and Tissue Engineering. Also has an active technical class benefit registered under the Technical Society of Student Activity Center in NIT Rourkela. The club conducts several activities around the year. The department also offers a high-quality regularization of skill development program introduced on January 24, 25 of sponsored by the Powerful Research Society India via advertised association with Delphi Club. The program aims to motivate young children to pursue research society's market plan. The institute offers a total of 60 seats for people each stream for the undergraduate under the BTech program, with joint seat allocation ability, direct admission of students abroad, Indian Council for Cultural Relations, and Ministry of External Affairs. Apart from BTech programs, the department also offers MTech, 2 years, and PhD programs to the graduates. Department of Biotechnology and Biovigilance of National Institute of Technology, Rourkela, was established in the year 2007 with the vision goal of delivering quality business by offering multidisciplinary teaching and research, developing world-class resources, and in making outstanding contributions in the realm of biomedical and biotechnology. Therefore, we have been expanding at a rapid rate. The department is divided into 3 streams: biotechnology and biomedical. There are 6 academic and research streams. Currently, a category of 18 faculty members from private schools have been appointed for carrying forth the department. The department is MBA accredited. We have various state-of-the-art labs too: biomechanics and biochemistry. Agricultural and environment engineering. Solar and molecular engineering. Achievements of the department include Center of Excellence in Tissue Engineering and Orthopedic Tissue Engineering and Rehabilitation. Program support in tissue engineering, program support bioinformatics, DSM, PIST, level 1.
Good afternoon, everyone. Once again, I'd like to thank guests, speakers in all the agencies participating. I'd also like to welcome the chairperson for this session, Professor Devendra Verma, sir, Assistant Professor from the Department of Biotechnology and Medical Engineering, NIT Rourkela. We have now reached the last session of the conference, and to begin with, I introduce Dr. Shamik Chaudhary, Assistant Professor, Environmental Science and Engineering Department, Indian Institute of Technology, West Bengal, who is going to speak on plant-derived nanomaterials for sustainable urbanization. He obtained his B.Tech from the West Bengal University of Technology, Kolkata, India, and M.Tech from the National Institute of Technology, Durgapur, India, both in biotechnology. He then earned his PhD in Environmental Engineering from the University of Singapore in 2017. His current research activities focus on the design and development of advanced functional materials with an emphasis on two-dimensional materials for sustainable energy applications in environmental remediations. Dr. Chaudhary takes keen interest in dissemination of his research findings and has authored or co-authored more than 60 scholarly publications, including research articles, review papers, and book chapters with over 5,000 citations. In addition, he has presented over 50 oral communications at national and international conferences. His research endeavors also include serving as an ad hoc referee for over 60 high-impact journals. In recognition of the quality, impact, and practical relevance of his research, Dr. Chaudhary has been honored with several intra and extramural awards, notably the Green Talent Award by the Federal Ministry of Education and Research, Germany in 2016. I would now like to request Sir to please begin with the presentation. Over to you, sir.
Thank you very much to the organizers of this conference for giving me the opportunity, and thank you, Ms. Malik, for the introduction. So, due to some technical problem, I'm not able to turn on my camera, but rest all is working fine. I hope that should not be a problem. So, as the organizers have already mentioned, I'll be talking today on plant-derived nanomaterials for sustainable urbanization. So, mainly what I'll be talking about is how we can synthesize graphene-based materials from biomass, mainly waste biomass, and how we can use that graphene that we can derive from waste biomass for addressing some of the sustainability issues that we are facing today. So as we all know that atmospheric CO2 concentrations continue to rise rapidly in response to increased combustion of fossil fuels. And if CO2 emissions continue to increase at their current rate, CO2 concentrations in the atmosphere are likely to rise to 560 parts per million by 2050 and could even soar to 1390 parts per million by 2100. So a vast majority of climate models also project that such dramatic increases would actually bring about catastrophic changes in the Earth's climate. And this can lead to major ecological and economic disruption in the later half of this century. Now, since projection of future climate conditions is dependent upon future concentrations of CO2 in the atmosphere, a massive effort must be immediately undertaken to reduce the amount of CO2 entering the atmosphere as much as possible. Now, there is a widespread scientific consensus and overwhelming political agreement that the development and deployment of a broad portfolio of advanced energy technologies would be the most suitable, potentially effective and sustainable approach to decarbonize our current energy infrastructure. And this will also help bring about long-term stabilization of CO2 levels in the atmosphere. Now, as you can see in this figure, energy efficiency improvements and increased use of clean renewable energy resources such as solar, wind, hydroelectricity, tidal energy, geothermal energy, etc., and other non-fossil fuel based energy sources, for example nuclear energy, they can actually are a long-term proposition of this portfolio. In the meantime, what we can do? In the meantime, carbon capture, utilization and storage, or CCUS, can actually provide a short to medium term technological option for mitigating anthropogenic energy related CO2 emission. Now, CCUS aims to selectively remove CO2 from flue gas streams of fossil-fired power plants and other large industrial sources and safely deposit the captured CO2 in secure storage sites or reuse it as a raw material in industrial processes. Thus, in the process, it can be kept out of the atmosphere for a prolonged period of time, maybe for over several hundred thousands to millions of years. Now, before coming to the technology in details, so the importance of CCUS as a mitigation technology under different future greenhouse gas emission scenarios has actually been extensively recognized and acknowledged and valued by the various energy agencies like the International Energy Agency, the World Energy Council, as well as the International Intergovernmental Panel on Climate Change, or the IPCC. For example, as we can see in this figure, in the IEA's or the International Energy Agency's 2 degrees centigrade scenario, CCUS is estimated to contribute 14% of the cumulative emission reductions through 2050 against a business to usual scenario. So, what is carbon capture and utilization and storage? Now, carbon capture and utilization storage is an integrated concept. Okay, so that comprises 4 distinct components. So the first component is capturing CO2 from the smokestacks of fossil fuel power plants and other high CO2 emitting industries, that is mostly steel, cement and fertilizer production industry. Then compression of the captured CO2 to a liquid-like state, that is the supercritical fluid, and transportation of the compressed CO2 to a suitable site. The site can be either onshore or offshore, and then directly utilizing it as a feedstock in several important industrial sectors, for example urea and chemical industry, food and beverage industry, then also for enhanced oil recovery and so on. Or we can actually store it by a natural or engineered trapping mechanism and monitor it as necessary. Now, potential storage options can include injection into deep underground geological formations, okay, or other industrial fixation or inorganic carbonates and so on. Now, the thing is, like, because of the widespread public protest across the globe regarding the safety of the storage option, the focus right now is more on the utilization of the captured CO2. So that is why I have labeled this slide as the carbon capture and utilization. The shift is now from CCUS to CCU, okay, because now the storage part, there is a lot of debate going on across the world. Many governments are skeptical whether the CO2 can really be stored underground for a long period of time. In the event of an earthquake, what will happen to the captured stored CO2? So because of all this, the focus is right now more on carbon capture and utilization. Now there are 3 basic approaches to capture CO2 from fossil fuel combustion. The first is the pre-combustion capture, that is CO2 removal prior to combustion. Then is oxy-fuel combustion, that is combustion in pure oxygen to produce a highly concentrated CO2 waste gas. And the last one, that is the post-combustion CO2 capture, that is CO2 removal following normal combustion. Now, if you see from the comparison of the 3 different capture scenarios in this figure, in this table over here, you would notice that while pre-combustion processes are primarily applicable to new power plants, and they can therefore not be applied to already operating facilities. And given the scenario, development or the construction of new coal-fired power plants is not being and actively pursued in most countries across the globe. So for pre-combustion capture suffers from this major limitation that it can only be retrofitted to new power plants. Then we have the oxy-fuel combustion systems, which is a near zero emission technology for both new and existing pulverized fossil-fired power plants, but the oxy-fuel combustion systems are still under development, and we will actually require significantly more effort to reach operational and commercial readiness. So among these three options, the post-combustion capture is the simplest approach for retrofitting to existing power plants and industries. So this technology is considered the most realistic choice, even though the efficiency of both pre-combustion and oxy-fuel combustion systems could be higher. So accordingly, now many different post-combustion technologies with varying degrees of maturity are currently under consideration. So first of them is separation with the use of absorbents or adsorbents. Then we have membrane separation, and we can also have cryogenic distillation. Now both absorption and cryogenic can actually inflict a parasitic energy penalty on top of the energy produced by the power plant. Okay. So as you can see from the comparison again over here, so both absorption and cryogenic processes can inflict a parasitic energy penalty on top of the energy that is being produced by the power plant. And most membrane-based gas separation processes are still in their infancy. Although a lot is being done, but still there is a lot of uncertainty about what type of membranes can actually be suitable for a long-term application in such adverse conditions that we usually encounter in a fossil fuel power plant. So in contrast, absorption on solid media actually constitutes an attractive option because of its reduced energy requirements and many competitive advantages, mainly simplicity of operation, then applicability over a wide range of temperature and pressure conditions, and low capital investment and moderate operating costs, and so on. So in view of these merits, absorption is actually being actively pursued by various researchers around the world. But to develop a suitable adsorbent that can actually satisfy the various performance targets for viable large-scale CO2 capture is actually a major challenge. Why? Let us look into a little bit more detail. So whenever we are developing a CO2 adsorbent, there are several key factors that need to be kept in mind. First and foremost is the material should be hydrophobic. Why? Because combustion contains a combustion flue gas contains a significant amount of moisture. So if the material must be hydrophobic, otherwise the water vapor that is present can actually compromise with the absorption efficiency of the material. Next, it must also have a high selectivity and capacity and selectivity. Why high capacity? Because high capacity will reduce the mass of the adsorbent that is required for a given throughput, and it will also lower the volume of the adsorbent bed and minimize the relative equipment size and cost. Then it should also have a high selectivity, because high selectivity towards CO2 against other gases will ensure that the CO2 component of the exhaust gas is completely removed for subsequent sequestration. Then it should have a moderate heat of absorption. Heat of absorption usually at the borderline between strong physisorption and weak chemisorption actually provides a good trade-off between selectivity and regeneration. Then next, it should also have a fast kinetics, because this will reduce the capital cost, energy requirement for operation, and absorption cycle time. So the adsorbent can actually be used for very short cycle time. So then comes is the chemical stability as well as the mechanical strength as well. Now high chemical stability under the conditions of capture and regeneration will maximize the adsorbent lifetime and reduce the replacement cost to a minimum. So this will have a direct impact on the overall economics of the CO2 capture process. And good mechanical stability will allow the adsorbent to be pulverized into fine particles and allow it to densely pack for maximum volumetric capacity. And it will also ensure that the adsorbent is capable of withstanding the bulk handling that is a feature of any industrial unit. Then of course it should have a low density, because then it can be tightly packed in the column, and above all, as the preparation cost. So the preparation cost is a key factor that must be kept in mind, because any adsorbent that actually will be used for this application must be inexpensive, so that it can be applied on a huge scale. Now there are many different types of CO2 adsorbents that are being explored. Some of them are zeolites, then metal organic frameworks, activated carbon, calcium oxide, lithium zirconate, and hydrotalcite. Now among them, the ones towards my right, that is calcium oxide, lithium zirconate, and hydrotalcite, they are the chemical chemisorbents, and in most cases their regeneration becomes expensive. So that is why physical adsorbents like activated carbon, metal organic framework, and zeolites are the most widely used, or more widely researched across the world. But if we look at a comparison of these existing adsorbents, the key problem with zeolite is that zeolite is extremely hydrophilic. So that is why it do not find practical application in a CO2 post-combustion CO2 capture system. Then we have the metal organic frameworks, or MOFs. Now MOFs, another key problem with MOFs is MOFs has a very poor stability in the long term, and it has a low tolerance towards other impurities that are present in flue gas, that is the sulfur oxide, nitrogen oxides, and it also has poor stability in presence of moisture. And then we have activated carbon. Although activated carbon has a very high capacity and low regeneration cost, the main problem with activated carbon is it has a very poor CO2 over nitrogen selectivity. Now nitrogen is one of the major component of the flue gas. So of course the material or the adsorbent must have a high selectivity towards CO2 over all other gases, especially nitrogen. So this brings me actually to the research that we have been trying, that I did past few years back. So that is the graphene. Now graphene, since its discovery, has attracted a widespread scientific attention, and because of its many fascinating properties. So graphene, as we all know, is a single atomic layer of sp2 hybridized carbon atoms that are densely packed into a two-dimensional honeycomb lattice. And it can actually be viewed as the basic building block for graphitic materials of all other dimensionalities. For instance, it can be wrapped into zero-dimensional buckyballs or fullerenes. It can also be rolled into one-dimensional nanotubes, that is carbon nanotubes, or it can be stacked into the three-dimensional graphite, the graphite that is present in our pencil. Okay. And due to its long-range pi conjugation system, this graphene is basically a pseudo-infinite nanocrystal because of its long-range pi conjugation, and as a result, it can offer a large specific surface area along with exceptional electrical, mechanical, thermal, and optical properties. Now, because of these fascinating properties of graphene, in fact, graphene actually satisfies few of the criteria that is required for of an ideal CO2 adsorbent. For example, graphene has a very good mechanical properties. So it is extremely stable. Its mechanical properties are extremely good for such bulk handling and industrial facilities. And then graphene is also lightweight. And then graphene also have a good chemical stability. Like sometimes in this absorption processes, the adsorbent is generated mostly through temperature and pressure swing. So in this case, it has a good thermal conductivity, so the graphene can actually be stable under such conditions. And above all, graphene is actually hydrophobic by nature. So graphene actually satisfies 4 out of the 8 criteria that are required out of an ideal CO2 adsorbent. But one of the major key technical challenges with graphene is its large-scale, cost-effective manufacturing. Now, currently, there are many technologies that are the most common techniques, rather, I would say, that are available to the fabrication of high-quality graphene. Mostly include micromechanical cleavage, epitaxial growth in ultra-high vacuum, then atmospheric pressure graphitization of silicon carbide, chemical exfoliation of graphite, and then the most famous one, that is the chemical vapor deposition of the CVD using transition metals as catalysts. Now, from an industry point of view, what we need to realize is like all these methods rely on depletable natural resources, and they actually often involve complex processes and sophisticated equipment that are difficult to scale up. So it is therefore highly desirable to develop industrially appealing and cost-effective processes for producing commercial quality graphene from renewable and sufficiently abundant resources. Okay, so this is the problem that motivated us to come up with a facile and general thermal graphitization scheme to obtain high quality graphene from naturally available inexpensive carbon sources such as oil palm empty fruit bunch, or the empty fruit bunch of the oil palm. And this technology actually does not require the need of any catalyst, substrate or solvent. Now, why was EFB biomass chosen? Now, EFB biomass is actually the empty fruit bunch, or the EFB biomass is a lignocellulosic agricultural residue that is largely available in several tropical regions of the world. That includes the West and Central Africa, Central America, Southeast Asia, and so on. And it is seldom converted to value-added products. Now, much of the waste is actually illegally burnt, thereby contributing to air pollution and smoke haze. So basically, these are the smoke haze episodes that I'm showing you in Indonesia, Malaysia, Singapore, and Thailand. So all these countries, because of the oil palm, of the waste oil palm fruit bunch, as well as the oil trees, are illegally burnt, mostly in Southeast Asia, mostly in Indonesia, and all. And the smoke that is generates from this the illegal burning can actually travel with the help of the prevailing wind and ultimately create a hazy situation in the neighboring countries. So if you see, this satellite picture is of Brunei. So over here, over here you can see how the satellite images are actually taken, and then how these smoke can actually travel. And this is the picture of Singapore. And Singapore actually have a problem of this smoke haze every year because of this illegal burning. So when I was actually doing my PhD, so I decided how we can address this problem. That was the main motivation of choosing this empty fruit bunch of the oil palm as a feedstock. And if the feedstock is not burnt, what is done? It is simply left to decay in dedicated landfills, ultimately emitting methane, which has almost 20 times the global warming potential of CO2. So utilizing the EFB biomass as a base feedstock to mass produce graphene can not only solve the waste disposal crisis in oil palm growing countries with potential revenue benefits, but it can also curb the unsustainable handling of the waste byproduct. So as depicted in this figure, so what the technology involves? The process specifically involves hydrothermal carbonization of the biomass into oxygen-rich hydrocharge and their slow pyrolysis into graphitic carbon. Now, compared to other existing methods like that are mentioned, the key merits of this approach are its operational simplicity, scalability, and low cost. And in addition, the method is environmentally benign since it utilizes waste lignocellulosic biomass as a precursor and does not involve any solvents or chemicals. Okay, so then what we did after the synthesis was done, we went for an extensive characterization technique. So the surface texture and morphology of the carbon material that we procured from the EFB biomass was extensively studied using state-of-the-art electron microscopes. So as you can see from the FESEM images, so we actually did the study at two temperatures. One is 800 degree and one is the 1000 degree. That is why they are noted as EFBG 800 and EFBG 1000. So this pyrolysis that we have done, so I have done at two temperatures, that is 800 and 1000, and accordingly we named the sample. So as can be seen, the FESEM images, so both the samples actually featured a smooth surface with layered structure. And this is because the tendency of polysaccharides to undergo carbonization under high temperature conditions to yield graphite-like structure is actually very well documented in the scientific literature. So it therefore actually appears from these type of images that conformational relaxation of the polymeric fibrils during the hydrothermal carbonization facilitated the formation of graphene layers upon their subsequent pyrolysis. Okay, then what we did is we looked at the high resolution transmission electron microscopy images. Now both the samples, as you can see, presented densely packed hexagonal domains and perfect hexagonal atomic order, consistent with those observed for conventional graphene layers. And in addition, the corresponding selected area electron diffraction patterns, or SAAD, that are being shown over here confirm the presence of diffraction orders that are characteristics of well crystallized graphene layers. Okay. And then what we did is, like, we also performed XPS measurements. So XPS measurements of both the samples were subsequently performed to gain additional information about the elemental composition. So the XPS survey scan generated photoelectron lines at binding energies of about 285 and 530 electron volt. So these are attributed to the C1s and O1s peaks respectively. And although the EFB biomass also contains other elements such as nitrogen, sulfur or phosphorus, so the lack of any additional spectral peaks actually suggests that no significant level of elemental impurities was present. So this confirms actually the near pristine composition of the EFB derived carbon samples. Okay. And what else we did? We did also TM image XRD analysis. We also did Raman analysis, and then we also compared the pattern or the characteristic parameters that we obtained from XRD for pristine graphene that is produced by the conventional modified Hammer's method, followed by hydrazine reduction, that is the sample GPN as marked over here. So we also did that and compared the values, and we saw that the Raman IDIG values, then the XRD despacing, so these were all, and then the despacing as observed from a transmission electron microscopy, these were nearly identical to graphene that is produced in the laboratory by the conventional technique. So because of this, we came to the conclusion that this material that we have actually derived from the waste biomass through hydrothermal carbonization followed by pyrolysis is actually a graphene material. So then, since absorption applications rely heavily on porosity and surface area, so we also measured the surface area and the porosity of the samples. So the samples that we obtained, so the sample that was obtained at 1000 degrees centigrade was at a higher surface area of 405 meters square per gram. Of course, this was not as high as the surface area of a theoretical graphene and theoretical surface area of graphene. And as you can see from the inset, and of course then we have seen the so in the inset you can see that the pores were mostly ultra micropores. Okay. So from the inset you can see that they are mostly micropores, and just if you see at the pore size distribution profile, you can see that these are the ultra micropores which we obtained through the NLDFA micros, that is the nonlinear density functional theory micropore distribution. Okay, so over there here we see that the micropore volume was significantly high. So 0.151 centimeter cube per gram for the EFBG material that we obtained at 1000 degrees centigrade. And subsequently, because of these fascinating properties, we were intrigued, and then we went on to measure the CO2 absorption capacity of these materials at 3 different temperatures of 0, 25 and 50 degrees centigrade. And at standard temperature and pressure, that is 0 degrees centigrade and 1 bar, all these samples actually presented significantly high absorption capacity of over 3 millimoles per gram. And another interesting thing to note here is, like, we also measured the isosteric heat of absorption, and when we measured the isosteric heat of absorption, we found that the isosteric heat of absorption at zero loading was less than 35 kilojoule per mole, and this isosteric heat of absorption gradually increased with increase in CO2 fractional loading, suggesting that lateral interaction between the absorbed CO2 molecules was mainly responsible for the absorption process. So basically there was a positive interaction between the gas molecules, and like it was more like initially a monolayer was formed, on top of which several other layers of gas molecules were formed. So with increase in surface coverage, the initial of absorption gradually increased. So to show you in a little bit more detail, so the isolated sites on the samples surface actually began to absorb CO2 molecules at low pressure, and as the gas pressure increased, so the coverage of absorbed CO2 molecules increased, forming a monolayer. And upon further increasing the gas pressure, the beginning of multi-layer coverage started, and small pores were filled first, and finally, with further increase in gas pressure, the complete coverage of the sample occurred, and all the pores were filled up. So what we also did was we also measured the CO2 over N2 selectivity. So for this, what we did is we measured the nitrogen absorption isotherms as well at 25 degrees centigrade. So the green plots over here, as which you can see, are actually the nitrogen absorption data. Now, so then what we did is since this nitrogen is usually present at a temperature at 0.75 bar. Okay, so in this case, so what we did is we took the nitrogen absorption value from the 0.75 bar corresponding from the isotherm beta, and for the CO2 we took it from the 0.15 bar. So from that we basically calculated, and we saw that the selectivity, absorption selectivity, is significantly high. In fact, it was about 60 in one case, and in the other case it was around 67. And these absorptive selectivity values are sufficient. Although someone can argue that my metal organic framework can have even higher selectivity. Of course, they can have even higher selectivity, but this values that I mentioned over here, these are sufficient to achieve a adequate CO2 separation from a flue gas system. So, actually, this work as I have already mentioned, we published it in RSC Advances. And eventually we also tested the recycling and regeneration of the material, and we found that this material can actually withstand several cycles of absorption and desorption. So we mostly regenerated the material with just by temperature variation, and eventually what we did is we tried experimenting with different other kinds of biomass that are readily available. So due to this time constraint, I am not showing all the other biomass that we have been that we investigated eventually, but this is one of the main pioneering studies that we did. So I was more interested to show you these studies, as it was also in alignment with the theme of today's conference. And this work actually got a lot of international attention as well. As you can see, it was awarded the Research Project of the Year award in 2015, as well as the Sustainable Technology Award in 2015 by the Institution of Chemical Engineers in Singapore. And then it also helped me win the Green Talents Award. In this award, it was actually being selected out of 757 applications from over 104 countries. So this award is actually given out by the German Federal Ministry of Education and Research. And right now in my lab in IIT Kharagpur, I'm also focusing more on different graphene-based materials, on how we can produce them sustainably. And apart from this CO2 capture, I'm also currently focusing on water treatment, mostly using graphene-based materials, mostly making them into a 3D form so that they are more easy to use, mostly in the form of aerogels and hydrogels or foams, sponges, and how we can use them as photocatalysts for water treatment. And I'm also currently working with other 2D materials like molybdenum sulfide, graphitic carbon nitride, and so on. So that is my key focus of research. But given the theme of today's conference, I thought that this would be the most appropriate part of my research that I can speak with you. So at last, I would just like to conclude by saying that we all know that we are plagued with a lot of environmental problems, and it is actually up to us how we deal with these problems. And we cannot deal these problems in an individual basis, but we all have to come together, and then only we can decide what we write next for the planet. That is the planet Earth. Because we have to realize that we have only one home, and we only have the resources that this only one planet is providing us, and so we should all come together to decide how we are going to utilize those resources in a just manner and in a sustainable manner. So thank you everyone for your attention. So if you have any questions, I would like to take them now.
I request the attendees to please put forward the questions, either in the chat box or you can just speak up and mute. Anybody?
Hello, I am Prasun Kumar. Samik, it was indeed a very nice talk on the green chemistry and the way how we can capture the carbon. I had a question that as you give an example of a biomass which could be converted into graphene. So is there a specific composition associated with the biomass which can be converted into graphene, or any type of the biomass could be converted?
Okay, first and foremost, thank you, Prasun. It was nice hearing from you. Okay, I wish this conference was you could do this conference in the physical mode so that we could actually meet, and it would have been really nice to visit NIT Rourkela. Now the thing is, there is no specific composition, but mostly the thing should be noted is over here that it should be rich in lignocellulose. So if the lignocellulose content is higher, then only we can get such rich carbon-rich materials. Especially in case of graphene-based materials, we have seen that if the lignocellulose content is high, so in one of the slides you may have noticed that there is this distinct hexagonal pattern that is present in graphene is usually seen. So if the lignocellulose content is really high, so that has been our observation when we have experimented with other kinds of biomass. So that lignocellulose, we are still not sure how it actually facilitates, but with those samples which have very high lignocellulose, though they are actually contributing to the development of such kind of a hexagonal pattern.
Oh, okay. Thank you, Samir. Thanks a lot.
Thank you.
Any further question? All right.
Thank you very much, Dr. Chaudhary, for the wonderful talk. My question is actually very fundamental, very basic question I want to ask. So you talked about the CO2 removal absorption before combustion, right? So my question is how, because CO2 is produced after combustion, so how CO2 is removed before combustion? Can you elaborate more on that particular process?
Okay, so so thank you, Dr. Verma, for your question. Now I'll just go back to this slide. So the one I was mentioning is actually about the technology that we were testing is actually the post-combustion capture. That is after CO2 is after the fossil fuel is being combusted. Now the technology that we are mentioning over here is the pre-combustion capture that I believe you are more interested to know. So in pre-combustion capture, what we do is like in the pre-combustion capture, the fossil fuel, mostly let's say it is coal, so it undergoes a process called gasification in the presence of air and steam, and it then goes some reformation. So basically it is based on the water-gas shift reaction. Okay, so in that water-gas shift reaction, what we do is like this burning this fossil fuel, if it undergoes that water-gas shift reaction, it will give us a CO2 stream that is rich in, that it will give us a flue gas that is rich in only carbon dioxide and hydrogen. So then the hydrogen can be used for power and heat, and the CO2 can be separated for transportation and storage. Okay.
Thank you.
Yeah.
Any more questions? All right then. Thank you so much, sir. Please accept our sincere appreciation for the outstanding presentation you made today. Thank you so much.
Thank you for the opportunity. It was a pleasure being here. Thank you everyone and have a nice day ahead.
Thank you. Next we have a presentation on neural bioprocesses in neurosurgery, and to speak on it, I invite Dr. Ravi Narayan Sahu, MCH DNB Professor and Head Department of Neurosurgery, All India Institute of Medical Sciences, Bhubaneswar, Odisha. Who's taking it? Excuse me. Okay. I request all others to please mute themselves. Only one person. Hello?
Am I audible?
Yes, sir, you are.
Otherwise, slides are visible?
No, sir.
Is it visible now?
No, sir, not yet.
I've said on the left side, on the microphone file, there is sharing button.
Yes, sir, there is.
Yes, I've shared it.
So can you reshare it? Yes, sir, it's visible now.
It's visible. Okay.
Yes.
So, good afternoon, everybody. I am Dr. R.N. Sahu. At the outset, I thank the organizers of this National Conference Bioengineering 2020, organized from NIT Rourkela in a webinar. And I thank the organizers to give me the opportunity to talk on this important engineering conference. Although I am a doctor, I am basically a neurosurgeon from AIIMS Bhubaneswar, and I work on brain, and basically we work on the clinical side. And yesterday I was going through some of the talks very interesting on this subject about brain-computer interface and other areas, and I find a lot of scope for clinical applications in this thing. So in this regard, I am giving just a short talk on neural bioprocesses in neurosurgery, what you are applying some cases, and what are the future prospects in these areas. So coming to the what are the processes, neural processes that we in a basic definition, these are the devices or the gadgets that can substitute a motor, a sensory, or a cognitive modality that might have been damaged in the brain. Basically, we all functions, all human beings function through a functioning brain, and the brain executes all the commands so that we can move our limbs, speak a voice, and also look into an object, hear a voice, and also a lot of articulations everywhere, and including we touch of the sense of smell, sense of the taste, everything depends on the functioning brain. So when there is a brain stroke or the part of the brain is damaged, a person becomes paralyzed or one important limb of the person get damaged, we cannot repair it. Brain is practically irreparable. We can only remove the damaged parts only. So that function needs to be restored in some way or other. Currently, there is no way to regenerate the brain tissue or other tissues. So we attach some artificial gadgets so that the patients can be mobilized or can be helped. Those are the what is called processes or bioprocesses, and when it is applied to the neurosciences, it is called neural processes. Currently, some of the existing applications in clinical sciences are basically the cochlear implant, which is an important thing for hearing. The function, if some person is born deaf or becomes deaf after birth, then the person cannot hear. So he cannot receive the sound of a vehicle or a horn of a car, something like that. So these are some implants that convert the hearing sounds, and they are inserted into the ear hair cells, so that up to some extent hearing function can be restored. These are some existing devices which are already coming to clinical applications. And another is the bladder implant. When the patients of paraplegia cannot maturate or pass urine, then this is also a bladder implant. Another applications we are using since 1980s, which we can patient with paraplegia or some lower limb dysfunction can sense the urination and also have a comfortable life. And similarly, a lot of artificial limbs have come up for a limb function or lower limb function, upper limb functions, and some of the feeding devices which are very self monitored can be taken. Another important thing is for the voice box. Laryngeal devices have come up. You can simulate or produce your voices based on some commands. And a motorized wheelchair is an important area. Yesterday there was a nice talk by one one of the speaker about how a motorized wheelchair can be integrated with a brain-computer interface, and so that whatever the patient thinks, he can be mobilized in a wheelchair in a better way. And regarding other organ replacements, like dialysis is another important part, which replaces the kidneys for their function. And especially in these COVID days, now we have ECMOs, what is that extracorporeal membrane oxygenation. When the lungs is functionless, we can also replace the lungs by some oxygenation membrane. And this is part of these are the devices which have come up already into the clinical applications. Some of the developing applications are now a lot of research is going on, like the bionic limbs. Basically, these are the cell command-driven limbs which patients or themselves can think of, and the limb will be according to their wish, just the way the brain functions. A retinal prosthesis is another area where a lot of research is going on. Whenever the patient is blind, he cannot see or she cannot see anything, then we can insert these things into a retinal layer, which can simulate some signals to the optic nerve and to the area of brain where vision is integrated or is processed. Then in that sense, even a blind patient can at least assess some part is moving and there is some light or not, something like that. And hopefully in future it will have more reformation going may happen in the innovations or invention. And another important area which is partly clinically applied nowadays is also brain stem implants, which is just similar to the cochlear implant of ear, where even the ear is totally functionless, the nerves are damaged in certain tumors. Then you can directly apply over the brainstem where the hearing function is there, so that a person can hear some sound also with these things. These are very recent things which have come up to clinical practice recently, but it's very expensive these days. And very few centers in India they are able to do these things. And one important area is we talk of the day is the computer-brain interface. That is the brain what we think can be processed in a machine, maybe in a sort of machine learning tools, then which can be integrated with another gadget, so that whatever sometimes the patients in a total paraplegic patients, they can think, and also they can think to process something, but they, in absence of a functioning limb or a leg, or in absence of a good spinal cord, they cannot execute. However, this brain interface, the computer brain interface PCI module, we can we can tell a machine to do the whatever we are thinking. It is a good things coming up nowadays. For example, moving a wheelchair or something like that. And similarly, the bionic tail presence is another things where the persons can look at the computer and some robotic arms can move. And some of the artificial organ replacement also be coming up with this type of gadgets. These are some developing applications which we are waiting for. Hopefully in future it will come. And these are some of the things just in a pictorial module I have given. This is the person with the upper limb functions, so it's not there, the limb is amputated. He can pick up a ball, something like that, with a bionic limb. A person with a vision loss, you cannot see anything, but with a sort of processes, retinal processes, you can process the vision so that he can see some areas. And this is an important cochlear implant devices where the hearing functions can be restored by a mechanized gadget. These are certain examples of bioprocesses which are coming up, and some are in existing applications also. So the cochlear implant, I was telling you, is one of the most successful gadgets nowadays, because when a person is born deaf, he is not only he or she is deaf, he is not able to hear sound. In absence of a hearing apparatus, he cannot speak the voices also. So the impairment of hearing is a primary phenomenon to the speechlessness, when the persons cannot speak also, because he cannot learn the speech actually. So restoring the hearing function is important for the persons to know the language also. So it is in childhood, when the child is born with inborn deafness, it is important to give some sound to the ears, so that the person will at least learn the language and subsequently he will be able to speak. Otherwise, in absence of a fully functioning ear, the speech will not develop. So this is one of the important aspects of the function of the ear. And now fortunately our government also, in case of in a child care initiative, they are also sponsoring the cochlear implant devices in children born with deafness. So these are devices which practically in simple way they convert the sound signals to electrical signals, which can be converted to a neural signal in the inner ear, and so that it transmits it to the brain, and the brain will integrate and also process the electro neural signal so that the patients know that some sound is happening, and subsequently you will listen to these sounds and subsequently try to learn the language, and the speech will develop. These are very important aspects, one of the few existing gadgets we are using. And similarly, the bladder implant, I told earlier, the bladder implant is for the persons who have suffered from the spinal cord disorder or spinal cord injury, when they cannot move around and also maturate, and urinary control is very important. And although this is one of the very few devices which is patented earlier in 1977, but they come to existence only in 1990s, and we are regularly using these bladder control devices, which helps the patients for the maturation function. And similarly, the rectal processes also, they have these things have come up recently with where you can place the implants on the back side of the eye, especially on the retinal fibers, where the lights will when the light will enter, and they will also transmit the electrical signals into the neural component, and the brain can process. And although currently the processing is not that refined, and it is the original figure where the persons receive it in a phase mode. However, now initially we have around 30% dropout. The person will receive up to in black and white, or at least some flashes of light will receive. But subsequently, with the development of the technology, maybe we are able to get a clear picture so far, because the integration of the electrical signal to neural signal is not as simple as it is shown in the diagram, and the things are coming up from the bioengineering side also. And currently, at least this will also help, at least the blind person can cross the road and looking at the lights of a vehicle, or some person moving or not. Currently now it is not possible. And so these are some big developing areas, and there is a lot of scope in clinical applications in this aspect. And another important part is the electronic durameter. As you know, the brain surface, brain is a very semi-solid organ. It's not it's a hard organ like bone, and it's a flexible organ, highly vascular, and it's packed with a liquid membranes. And so any hardware component you cannot apply on the brain. Practically, it will erode into the brain, and it will sink into the brain substance. So fortunately, our brain is surrounded by a little tougher covering, which is called durameter, and the durameter covers and shapes the brain in normal conditions. And so the electrical or electronic devices we sometimes apply on for cases like Parkinsonism or things directly on the dura. So dura can be replaced with some artificial membrane also, because it's a covering only, it doesn't function anything. So it's an important thing now. The recent development is coming up in the replacing the dura with a e-dura, what is called electronic dura. So basically, it's a software just like a circuit board or PCB type of things, where we can instead of a natural dura we can place on the natural surface of the brain, it can receive the electrical signals, the neural electrical signals from the brain, and process in a remote gadget, so that whatever the brain is thinking or the brain is executing inside, it can be converted to a pattern or a signal where we can learn and we can process for subsequent BCI. So these are new developing areas, and some areas we are using in certain cases of to monitor the pressure inside the brain. For example, in case of a brain tumor, whether the brain is swollen or not, we are measuring those things currently. But these are having a lot of scope in future. And these are the things, some of the devices which converts the electrical signals to a pattern. Then we can also manipulate those things to control the limb function in primates. These are certain cases who have been experimented in lower animals, where in case of a spinal implant, spinal cord is damaged, and we can still achieve some function of the lower limb by regulating the spinal cord control with the help of electrical or electrochemical signals. So a lot of things are also coming up in primates, like robotic postural process. For example, in a small mouse, we have even the spinal cord is damaged, we place some electrodes on that, and we can learn the limb movements, how it is happening, and subsequently program it with the computer, and also we can give some electrical, just like this here, this Dura matter, this E-Dura was placed on the spinal cord, and some chemical stimulation after calibrating, you can process that so that the animal which is paralyzed can be controlled externally with the help of some devices. So these are developing areas which is not yet come to the clinical practice, but it shows a tremendous scope in doing so in future. So these are certain areas also, the bionic telepresence, where the brain is damaged, the patient is totally paraplegic, not able to move the limbs. Still, with the help of external devices, where the EEG signals are processed, and what these things are, that now it can be processed over a computer, and then it can be reprocessed with some other gadgets, so that the wheelchair can be moved, or what is the person is thinking can be manipulated by remotely or externally. These are these new things are coming up in a bioprosthesis field, and this will going to help in a big way if things are the invention is complete. So these are another area is the cognitive enhancement is like some we are apart from this, we are learning many things in life also, just like we are learning how to drive a car, or how to learn to pilot an aeroplane. Okay, so these are these areas we can simulate and develop models, and which area of the brain are really working on, so that the person who is driving the car, what happens he met with an accident, what happens if he is doing the drunken driving, and what parts of the brain are responsible for this thing, so that we integrate these things into the system, so that we learn that these are the areas can be manipulated. So these are all things of cognitive enhancement. That means how we can think of enhancing the capability of a person for an optimal performance. These are areas which are developing so that we can manipulate if necessary for a person. So these are some of the other areas how even our brain signals like speech and other things can be integrated, and we can learn to decode or code that areas whenever we are functioning. Basically, much of the brain function on its own way, and it is not possible to know which area is functioning in each person, because every person's brain is different. Although it's an organ made up of flesh, but just brain is a different organ in different perspectives. Suppose every person's kidney, for example, function in a similar way. Every person's heart function in a similar way, but the brain are the different things for different person. A person becomes a different person because of his ability to think differently. That is the thing. So we can learn differently how a person is thinking by coding his electrical signals over the brain, and so that even the patient's particular patient suffers from a stroke and is now not able to speak some certain things, then we can learn what are the lost signals, and we can decode it. And if this can be manipulated over a from a hearing side like human auditory cortex or something like that, we can give that person's to ability, again the ability to speak words. So these are certain coding and decoding of the cortex. Now the lot of experimentation was going on in different areas, and as I told earlier, BCI is an important aspect which is a system that creates a non-muscular channel for relaying person's intention to an external devices, and this the person's what is thinking can be processed on a machine, and subsequently if you get a pattern, then a machine learning tool can be applied so that in persons with disability you can help it, and mostly it can be invasive or non-invasive. By invasive means we can apply directly on the brain surface with the brain surgery, and so that we can directly record the signals and processes. Or it's not, we can wear a helmet made up of things, but the helmet things are not that fine signals you can get. Or the invasive things is more accurate. But in absence of a invasive, which is very expensive, also riskier, we can use a non-invasive methods. So these are certain applications that are coming up, and which is very a computer-based neural processes or some smelling device, virtual environment, and other interface you can do. And there are another things is it's of immense help in rehabilitation also, where the persons who are not able to move limbs, they can move limbs with the help of a different mechanical, electromechanical processes, and the patients can, with the movements of the eyes or movements of the face or tongue, or simply by thinking, he can move the legs in a different. He also can, even now these things are coming out, whether he can feel pain or temperature variation outside also, and so that he have a, as far as practical, have a complete functional life, even with the loss of the limbs or paralysis or paraplegia. So these are all things, and another thing is extended mind thesis, which is a concept by Dylan Clark's, and where can be even our mind functions can be estimated externally, just like the way sometimes we think and write notes on things. We remember sometimes that by looking at a gadget that our notes are then in that computer, that printer, or maybe in that almirah. So we sometimes associate our things with external things. Similarly, our brain also can associate things in a different way. So this is an extended mind thesis which can be, by thinking, you can integrate into a machine, and so that it can be stored outside also, all the functionalities. So similarly, now the bionic hand has come up, which is important, just like we use a fingerprint sensor in a computer, and you can use in a paraplegic limbs with some sensor, so that you can able to touch a gadget and know that this rough or smooth or whatever, or maybe you can know whether it is a fruit or some other ball. And this is beyond the motor function. Now we have extended our the thinkings to know the actual texture or sensation also. So this is the example of a bionic hand which are coming up. It's not yet used in clinical practice, but a lot of experimentation is going on, and hopefully in some day we will come to these things. So this is another area where a person has a lost limb, and his brain is functioning nicely, the nerves are functioning, but the limb is lost. So that you can add a artificial limb which can have a bionic fingertip, and which can know the surface roughness or fastness and temperature variation, so that even touching the surface, the signals are processed and through a computer-based devices, and can stimulate the nerve and directly, so that we know that this is the area which I'm looking at, touching that area. So this is of good use, because we are neurosurgeons. We can attach these devices if it is really functioning to the nerve, because the nerves are the surgically accessible areas, and we can attach these things so that the patients which is with a loss of limb can also function the limb, and or maybe he will able to help himself in a big way. So these are just like things, and the bioprocess has come in a long way for specific neurorehabilitation tools, like in cases of the spinal cord injury, because every year we get a lot of patients with severe spinal cord injury or brain injury. We are not able to help in current treatment practices, and patients suffer from brain stroke. They have they require some intelligence or cognitive enhancement tools also, and sometimes some limbs are they have a paralysis, and we can help them. So these are all the gadgets will be very useful in current practices for patients with blindness or some loss of bladder control, or they are not able to hear or some look into the objects because of the blindness. So there are a lot of scope in rehabilitation, and of course the stem cell research has come in a long way. Now they are showing some promising results in repairing some up to some extent the nerve cells which are damaged in surface, but they cannot restore the function. At least they remain viable for a long time if they are damaged. So these are all areas can be integrated with a bioprocesses, so that the bioprocesses works nicely. So to conclude, neuroprocesses is a fast developing area, and the brain-computer interface and machine learning, etc., will shape the future invention. But we can say we can look as a neurosurgeon, I can look into those areas maybe. And e-BIRA is a nice thing, as I have explained, which is the covering of the brain, which will help us to learn the whatever the brain is processing in terms of the decoding area, and so that it will have a potential to do in a mechanized way for an artificial limb or any prosthesis. So this is a talk I am just given so that this is a bioengineering conference, so that a lot of people are, I expect that they must be doing research in those areas, and we are here to help them for purpose of developing models for clinical applications. That is the purpose of this talk. I hope I have conveyed the message. And this is another recent advances where the one paper published from for neurological focus, how a rat model, albino rat, can be monitored externally with the help of a electrical signals stimulating is nice-to-stable pathway, so that we can control the brain from remote area with this one example. These are all experiments done in primates, and so this a lot of scope is there in brain surgery. I can hope that, and so thank you for patient listening. Any questions I'd like to answer also.
Any questions?
Thank you, Dr. Sahu, for the wonderful talk. So my question is, how long basically these brain-computer interface are going to be in direct contact with the body, and are there any side effects, long-term side effects or short-term side effects of using this brain-computer interfaces?
Actually, these are all external devices. Or for us, we use a lot of foreign material on brain. Actually, for example, we use a lot of suture material over brain. For example, we are using something to tie the skin inside, which stays long. We are also applying, for example, while operating on the brain, you need to remove the bone flap first of a skull. Then we fix the bone flap with screws and plates, meaning the titanium plates and everything is fixed. So already we are doing using a lot of foreign material over our natural body. Okay. For example, we are using a dental implant for denture, or maybe we are using a lot of titanium implants over the bone and in area very near to the brain. Even inside the brain, we are also using for draining the brain fluid, that is called CSF, to abdomen, other areas. So we are using a lot of silicon material, everything. A lot of silicon tubings inside the brain also. So far, when they are very compatible, biocompatible within the brain also. Many persons are moving in outside also with some brain implants inside. So attaching an implant into the brain we have a lot of experience and nothing happens. Mostly nothing happens unless the material is not really bioreactive. Okay, but platinum is a good example, which is very biocompatible, and a lot of biocompatible material are there also. So even in our ICU stay, we sometimes need to monitor the brain functions with the help of certain things like brain pressure monitoring or ICU monitoring devices, which are basically electronic gadgets. We use at least 3, 4, or 5 weeks also. Of course, there is a chances of infection, but not it is as infections around 5 to 6% happens because of, it's not because of the device itself, it's because of the bacteria or other things, which is the infection occur. Infection may occur in any normal brain also. So apart from this, if the material is inert and it is not bioreactive, we can use for longer period also. So regarding how the brain will behave to the material depends on that things. I hope I have answered your query.
Yeah, thank you.
Any more questions? All right, I believe there are no more questions. Thank you, sir, for sharing your knowledge with us here today. Thank you so much.
Thanks a lot.
For the next presentation, I would like to welcome Dr. Indranil Banerjee, sir, Associate Professor, Department of Bioscience and Bioengineering, Indian Institute of Technology, Jodhpur, to present on pro-angiogenic nanobiomaterials for bone tissue engineering. I am proud to introduce Sir as a former professor of biotechnology and medical engineering department at NIT Rourkela. His expertise in the field of microfluidics, tissue engineering, regenerative medicine, biomaterials, and theranostic systems. He completed PhD from Indian Institute of Technology, Kharagpur. Recently, he is an associate editor for the journal Frontiers in Medical Technology. He has overall 1633 Google citations and 456 citations in the current year. He was awarded the 2018 JNCSR Visiting Scientist Fellowship in 2013 and also has been a guest scientist in Max Planck Institute of an Intelligent System, Stuttgart, Germany. I would request you to begin with the presentation, sir. Over to you.
Okay, thank you. Thank you for this nice introduction. So first of all, I would like to say that I'm very happy. So it's almost an virtual homecoming for me. And I would like to thank my former colleagues there. So Dr. Anju Babu, Varma sir, Dr. Bala, and I think many of new faculty colleagues have joined there. So please consider me as your friend. And there is a best wishes from your friend from IIT Jodhpur. Hello?
Yes,
am I
sir.
audible?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay. So now I'm going to present this one. So I just need to, just a second, let me share my screen. Is my screen visible?
Yes, sir.
Thank you. So I would just like to mention that there might be a little bit miscommunication. So the title of my talk is that angiogenesis in tissue engineering. Okay. So let's start. Now, already that anchor has told you that what is my domain of research. So I mostly work in the domain of tissue engineering, drug delivery, therapeutics, theranostics, biomicrofluidics, and mechanotransductions. These are the area. In the case of specifically in tissue engineering, I work in the domain of angiogenesis or engineering angiogenesis. So today, the outline of my presentation is like this. So first I will just give you an idea that why this angiogenesis is so important in the present day tissue engineering, and then a bit of overview of angiogenesis, and then I will go to the two of the different approaches that my lab used to adopt and work on. So that is engineering angiogenesis to biomaterial based approach and engineering angiogenesis scaffold based approach. These two are a little bit different, and I will explain these differences in detail. So now, so first the question is why angiogenesis in tissue engineering, why it's a big deal. Now to start with, if we go for a little bit an informal way, I'd just like to quote a part of a conversation that was being recorded in 2019 June when on behalf of the World Economic Forum. So Dr. Daniel Hill, the lecturer of biomedical engineering, University of Melbourne, so interviewed one of his senior colleague, so Professor Andrew O'Connor, which is a renowned tissue engineer, and this is the same university. And what the question was a very interesting question, and probably one of the most fundamental questions those who are working in the tissue engineering. So question was, what are the main roadblocks that are preventing tissue engineering from making a bigger impact, and how can this challenge be addressed? So the answer of what Dr. O'Connor gave at that time was very simple and straightforward. The answer was that, so one of the biggest challenges is the vascularization. So now let me explain these things in a little bit details. So objective of tissue engineering is to prepare an organ or tissue in the laboratory condition and then implant the same in the body of the patient who requires it. It can be any kind of tissue or organ. So this is the fundamental approach. Now the moment you want to make this, very important point is if your tissue or organ contains the live cells which are supposed to be, then the moment you implant it in a body, so it needs a continuous supply of nutrients and oxygen. So question is how to ensure that unless there is a formation of new blood vessels, that cells that are present in that engineered tissue or organ will eventually die over a very short period after the implantation. So, but the problem is, whatever approach so far people have tried, none of them are very foolproof or been able to vascularize an organ which is of a clinically significant size and dimension. So technically, there are certain level of success making artificial blood vessels, but that is just to prove that the blood vessels can be made in a tissue engineered organ, but it is not supporting the exact purpose for which a blood vessels is needed. So that is the point Dr. Connor tried to highlight in that. Now in the same context, eventually it has been noticed that it is in that bottom graph image, you can see that it's a screenshot of that NASA's website. So in 2019, NASA launched a similar challenge. That's a very interesting thing. It's a very high value. So you can see that the value here. So it's a very high value challenge where NASA is actually asking to the scientists if they can come up with something, a fully vascularized tissue. Because they have also realized this is the future of tissue engineering. Unless we are in a position to surmount this particular challenge, we won't be in a situation to make tissue engineering as a clinically viable clinical alternative. So because of this too, so angiogenesis is nowadays one of the key focus in tissue engineering research. Now question is that what is the limitation? So if we go into a little deeper from the try to understand from the mechanistic point of view. Now this part, please follow this cursor in this left side of the schematic. So you can see that I'm just trying to represent that the normal in vivo situation where these red lines are representing the blood vessels and these circles are representing the cells. Now if you see, what is very interesting is that inside our body, most of the cases, the cells which needs a very high oxygen and nutrient demands, they generally reside somewhere within a 200 micrometer away from this blood vessels. Now, why this 200 micrometer? This particular value is have a very high significance, because this is the diffusional nutrition limit. So this diffusional limit is somehow governing whether the cells will get nutrient and oxygen supply or not through the diffusions. Now here you see there is another cell. I just marked it in a different color. So it is more than 200 micrometer away from the blood vessels, and it is expected that these cells will eventually die if it needs a high oxygen or nutrients. So our body has a mechanism that can actually take care of this particular problem and make sure that there will be a formation of a blood vessels near these cells, so that they never die because of the lack of oxygen or nutrients. But when we are going to make the tissue in a laboratory condition, the problem is many cases an organ that we are aiming to prepare has the dimension many-fold bigger than this 200 micrometer. So the cells which are present at the, say, interior of these organs, so for those kind of cells, it is almost impossible to get adequate nutrient and oxygen supply from this through only diffusion. So here we really need to ensure that the vasculature should be there. Unless we ensure a vasculature or similar kind of active transport process, the survival of these cells will be an issue. So that's why the angiogenesis is very, very important in tissue engineering. Now, if we go to the angiogenesis, just to understand in a native condition or this physiologically, how this angiogenesis happens. So, before going to angiogenesis, let me just tell that inside our body, the formation of blood vessels can happen through two processes. One is known as a vasculogenesis, which is associated with that developmental process. At the time of development of embryo, that time the vasculogenesis was one of the methods. But the moment people start say that embryos start developing, and then that new neonatal born, and then they grow, the process of formation of blood vessel becomes mostly rely on angiogenesis. The earlier notion was that in the adult, angiogenesis is the only way of formation of blood vessels. But nowadays people have found out that it's not the sole mechanism. Even vasculogenesis also contribute, but still angiogenesis is the key process that governs the new blood vessel formation. Now there are two different kinds of angiogenesis that governs. One is known as the sprouting angiogenesis, and sprouting angiogenesis means that the formation of a new blood vessels. So please follow the cursor. The formation of a new blood vessels from an existing blood vessels, but in the form of a sprout. On the other hand, there is an intussusceptive angiogenesis, which is basically the cleavage of an originally existing blood vessels. So here one tube that gets say forms in cleavage and becomes segregated into two different blood vessels. So these two are the common format of forming blood vessels. It has been observed that the intussusceptive angiogenesis is generally happen in a resource less resource domain, where the number of cells capable of contributing to angiogenesis is less. On the other hand, sprouting angiogenesis is the most common one. Now, in the sprouting angiogenesis, it follows a couple of, it's a multi-step process, involves that coordinated interactions of many cells and many biomolecules. So it starts with the enzymatic digestion of the basal membrane, and then there is a formation of a tip cell and stalk cells. So these two particular selection of cells is actually the key event in this angiogenesis. So if you look into that schematic, you can see that there are many different kind of cells, or rather I would suggest that there are a number of endothelial cells which is making that lining of blood vessels. Out of this all endothelial cells, one cell will become eventually the leader, which will govern the direction of the sprout, and these cells are generally termed as a tip cell, and then these cells were followed by some cells which are termed as a stalk cell. So what happened in vivo condition, So when some cells started experiencing a lack of oxygen or nutrient, so a situation which is often been termed as an hypoxic situation inside the tissue, in the response to this hypoxic condition, they started expressing one growth factor known as VEGF. There are a number of mechanisms involved for secretion of this growth factor like ionos or HIF1 alpha. So this growth factor VEGF is an chemoattractant for this endothelial cells and corresponding sprouting. So let me go to that even a little more details of this experiment, this phenomena. So what happened here I am showing this one. So suppose there is this particular zone, what I am showing VEGF, say this is the zone where there is the most oxygen poor region. So the cells present here, any parenchymal cell present here, will start secreting the VEGF, and those VEGFs will act as an chemoattractant to these cells present in that blood vessels, endothelial cells, and these endothelial cells will start forming the sprout, will be supported by the stalk cells, and then they will move towards each other, and eventually there will be a diffusion and finally formation of blood vessels, and these blood vessels in later phase will get matured with the participation of the pericytes or the mural cells. So altogether this is the phenomena how a blood vessel forms in vivo. Now this particular phenomena, I should not say that the tissue engineering actually tried to make the copy of it, but it has started long before related to cancer research and our developmental study. But the later people have found that even in vitro condition, some part of this mechanism is possible to replicate, especially this fusion portion, that endothelial cells in an in vitro condition can fuse to each other, a process often been termed as anastomosis, and then can make a particular blood vessels. So that kind of understanding and evidence actually make the scientists enthusiastic to explore this possibility for tissue engineering application. Now here, so on the basis of that, several different kind of approaches been taken so far to engineer this tissue engineering, this angiogenesis. In the next section of my talk, I will now focus mostly this angiogenesis related to bone tissue engineering, because bone tissue engineering is my area of work, and as well as the angiogenesis. So it will be easy for me to present this angiogenesis in the context of bone tissue engineering. So angiogenesis, as I have already mentioned, that the angiogenesis is crucial for any tissue engineering application. So is the bone tissue engineering, maybe even more critical for bone tissue engineering, because bone is a very vascularized tissue, but it is difficult to make them vascularized. Now this is the structure of the bone. If you see that there are a lot of blood vessels that enter into the bone, and now question is, when you are going to make this, engineer this bone, so here is the schematic, I am telling that this is a broken bone. Suppose a tissue engineer wants to make an implant that will actually restore the integrity of these particular portions and will serve as a native bone. So he starts here, suppose he has adopted a tissue engineering approach. So what he will do, so he will first prepare a scaffold. So this one is the scaffold, and then this scaffold will then be populated with the appropriate types of cells, suppose osteoblast, and then they will try to implant this one in this broken portion. So the moment this approach, if we really follow, then what will be the consequences? So things will be something like this. Now, if the moment you place this, say your so-called artificial bone in this wound site or defect site, now there is a requirement that this thing should get integrated with the rest of the part. And this kind of integration will get impaired if there is not adequate angiogenesis. Now, if the angiogenesis is not there, then the vasculature won't form there, and as a result, what will happen? The cell will die inside this implant. There will be poor osteointegration, and there will be a clinical situation which is known as atrophic non-immune. Now, question is that how we can make sure that this scaffold won't fail or how we can ensure that there should be an adequate angiogenesis. So far, the approaches that has been tried by the different research groups are, the first one is the application of angiogenic growth factor. So I showed you that earlier in, say, mechanistic approaches, that the VEGF is the key growth factor that promotes the angiogenesis. So one of the very common approach in angiogenesis is to directly use VEGF or another growth factor known as platelet-derived growth factor for that. But the problem with this kind of growth factors is a very short half-life, they are very high cost, and 3D distribution is very difficult to control. Another approach is the cell-based approach. There people are directly applying, suppose in case of bone tissue engineering, along with the osteoblast, people can directly apply that endothelial cells there. But the problem is endothelial cells, depending upon the source, they varies a lot. Varies means there will be a very much vary in the phenotype and in corresponding your angiogenic potential. And the source wise there will be a lot of variation. And second important problem is that how to co-culture these endothelial cells with the other cells that are required there. Another approach is a preformed architecture. So preformed architecture of blood vessels like channels inside the scaffolds. This are generally being achieved by micropatterning and through microfluidics, but these are very sophisticated and needs a costly infrastructure. Then another approach is gene therapy, so targeting specific host cell, make them competent to create more angiogenic growth factors or to respond to the angiogenic growth factor. But we all know that, like in all other cases, gene therapies, people are still skeptic with the gene therapy, and there are a lot of issues which needs to be resolved before going for a clinical practice. So question is that what could be done? So here our group has been working in with this particular problem for say last 7 or 8 years, and we are looking for some alternatives of these approaches that I mentioned just before. So our proposition is two. One is either you look for a pro-angiogenic biomaterial or you look for a pro-angiogenic scaffold. Now when I'm saying this, what I'm trying to mean is either you make your scaffold with such a material that the material will induce the formation of VEGF or other factors that are inducer of angiogenesis. Or otherwise, you make a scaffold where your material may not be angiogenic, but the microarchitectures and the microenvironment is such that will promote angiogenesis. So this is the basic difference when I am saying one pro-angiogenic biomaterial and pro-angiogenic scaffold. So in this regard, now the big question is how to get it or how to make it. So the first approach what we've adopted for this was the use of selective group D metal ions like cobalt +2 and nickel +2. Now here I would like to mention that use of this particular group D metal ions, the rationale behind is that these kind of metal ions are somehow able to say instruct the cells to create an environment which is analogous to an hypoxia environment. So technically they are not reducing the oxygen content, but what they are doing is that they are activating the same enzyme system inside the cells which get activated when there is a less oxygen. So it is a hypoxia mimicking factor. So this kind of ions can do that things very effectively. And we thought, why not to explore these ions and use them in our biomaterials in a controlled manner, keeping a very cautiously by considering their toxic limits. So if we want to use this one somewhere much below than their toxic limit. So now I am not going into the details of this mechanical pathway, but mostly what they does is that they activate this HIF1 alpha pathway. HIF1 alpha is a transcription factor for this VEGF, and once HIF1 alpha pathway gets activated, it activates VEGF and promotes the angiogenesis. Then the second approach in this regard is to use some natural molecules, which is very cheap and easily available. So the one such molecule is in gum tragacanth. So this is a natural gum and it shows some potential. I will come to this point later. So this one is in polysaccharide. And the third approach, these two approaches are pertaining to that engineering angiogenesis using biomaterials. And the next one is engineering angiogenesis with the scaffold. Here we have adopted an hexagonal closed pack 3D scaffold. So this hexagonal closed pack 3D scaffold is something different, and I will come to this again in details when I will go to that particular topic. So when we said that we can play with this group E metal ions, so we needed one template material which can be manipulated with this metal ion. We thought that why not the most explored and well-established material that people have tried so long with limited success and try to improve its property. So we picked up the nanohydroxyapatite. So nanohydroxyapatite, we all know that the hydroxyapatite is the inorganic part of our bone. So this material is mostly a calcium-based apatite material. And now our approach is to, if we can replace some of the calcium present in that hydroxyapatite with that metal ions we are talking about. So this is the key features of this nanohydroxyapatite. They are biocompatible, non-immunogenic, osteoconductive, and chemical and structural resemblant with the bone apatite. Another approach is that if we can tap this hydroxyapatite with the biomaterial, just like gum tragacanth that we are talking about, and tap this gum tragacanth with this hydroxyapatite crystal and make them more proangiogenic. So here is that outline of the work. So first one is the synthesis of the doped nanohydroxyapatite. Here we work with wet chemical methods. So these methods are well-established methods of the hydroxyapatite synthesis. But what we did at the time of making this one, we doped this nickel +2 in the system, keeping this metal ion phosphate ratio fixed. And so these are the different kind of doped hydroxyapatite, nickel doped nanohydroxyapatite. And here are some physicochemical characterization. So we performed a lot of physicochemical characterization. This part has already been published in RSC Advanced. So we did a lot of physicochemical characterizations. I am just showing a few here. So here we showed that what are the structure of this through FESEM, then TEM, and then here you can calculate we calculated the ferrite diameter, and then we calculate the extent of doping through ICP-OES. What we observed that we thought to dope the materials in a ratio of 1, 5 and 10% weight by weight, but when actual doping happened, we received something almost quite less to that original one. So that is quite obvious that you can't expect an almost theoretical doping, but this is the doping. So finally what we know that whatever the bioactivity we are getting, that bioactivity is coming from this doping percentage and not for this one. So that understanding is very important. Then we perform that XRD and FTIR. So our main objective to perform this one to check whether such doping has any significant effect on the crystal structure of the hydroxyapatite. So we did not found much variation in the crystal structure. I did not show that all the crystal parameters here, but we checked that and we did not get. So the next point what we did, we checked when we were using this particular hydroxyapatite, how that bone cell form or a response of the bone cells. First one is the formation of the nodule. So in the case of N10 half, where we have say almost 2 point some percentage of this hydroxyapatite nickel doped, we got a good nodule, which one is an say classical example of the maturation of the bone cells. Similarly, we also check the expression of an factors. This green one is the rungs one, some differentiation factor of this particular cell, and then we check corresponding. We also check these things through RT-PCR, and then check the proangiogenic property of the material. So here we observe that the moment we dope the nickel, the relative VEGF production by the cells get increased manifold. You can see that there is a huge and continued, say, dose-dependent increase in the VEGF production. And similarly, when we check that what is that upstream signaling of that, we check that there is an HIF-1 alpha production also increase. So these two confirm that the moment you add that engine HIF-1 alpha, there will be an increase in this corresponding VEGF production and as well as your by HIF-1 alpha pathway. Then we check how these cells or how these materials are commanding that endothelial cells to form the tubes. So here we found that when you are using these things, there is a more network formations among the endothelial cells in comparison to the normal half. But eventually what we observe that it is N5 which is giving better result rather than N10. And then we also calculated the number of tubes, average tube length, all. In the next set of work, we work with this, what I mentioned previously, we tagged it with that gum tragacanth, and then we make this nano hab and we check how much conjugation was there through thermogravimetry. And then the similar way we studied how this nodule formations is happening, what is the cell proliferation, whether they have any effect or cell proliferation or not, or any effect on that cell cycle or not. So here we did not observe much difference. They are just like a normal hab. And we check this, when we check with that human mesenchymal stem cells, we observe that there is an increase, may not be very high, but there is an increase in that. In case of PG-HAP, there is an increase in the alkaline phosphatase synthesis. And then we check the proangiogenic properties. So when we check the proangiogenic property, we see the relative VEGF expression is also high, so almost 1.4 times, and there is a formation of this network, which is very, very prominent in case of PG-HAP. Now the next approach was the hexagonal close packed bead arrangement. So here in the first schematic, I would like to show what we actually tried. Now hexagonal close packing is a very common packing arrangement in crystals. In the crystals, atoms are often being arranged in that format. But that particular approach has never been mimicked for the other kind of scaffold fabrication. So here we thought that if we take a bead as a unit analogous to an atom, and then if we try to make them in an hexagonal close pack format, what will happen? Now question will come, so out of the blue, why you want to go with such kind of approach? Now the very interesting point is, these beads, what I am showing here, these beads are basically macro beads. So they are not micro beads. But the moment you place them in a sequence following the hexagonal close pack arrangement, they will start generating some pores between them. And this pore volume and pore diameter will eventually remain fixed. You cannot change. If you have an spherical bead, then the pores in between will always follow a particular dimension, and you can control that pores out of micrometer, say, dia, and you can control the pore diameter with that. So here I am giving an example. If spheres of a radius r are arranged in hexagonal close pack, then there are actually two different kind of pores being formed. One is known as a tetrahedral pore and another one is known as an octahedral pore. That the radius of this pore will always follow this relationship. So 0.225R and 0.414R. And the overall porosity of this system will remain fixed. So now you can understand that the moment this has been a simple, follow this simple relation, then by changing the R value, you can generate the pore size inside the scaffold by yourself, and you can manipulate and tune the pore size. So when we go for this is the similar things what we are talking about. You can see that is the structure of this scaffold. This is the hexagonal close pack arrangement. This one is looking a little bit distorted because this one is the freeze-dried version. And here, this is that wet condition. We are showing this pore structure. What is an octagonal and what is the tetragonal pore. So in case of say tetrahedral pore, 3 at the bottom, 1 at the top. And in case of this octahedral, so this 3 and top being covered by another 3. So these are the unit of this octahedral and tetrahedral. Now what benefit this kind of structure will give? Now here, if you, I would like to go back one more time. So here if you see this, now this is the pore. What is an important parameter for scaffold fabrication? Now these are the bead, and we are making it in a layer by layer fashion. So my point is, if I can put any kind of bioactive agent at a particular location, so I will having a control over its spatial distribution. So any bioactive, I can have and control, I can put multiple bioactive materials entrapped inside a bead at different location, and then can create a gradients of different growth factors or bioactive molecules inside the scaffold along with the defined pores. So here we did some drug-related study with this. So here you can see that we use the model rhodamine as a fluorescent dye. This is the scaffold. So this one is the first one is a 3-layer and another one is a 5-layer system. So what we did, we placed this particular rhodamine loaded scaffold on an agar plate, and we just let that rhodamine to diffuse. And now you see, and we check the diffusions under a fluorescent, say, illuminated stage. And then you can see that there is a continuous diffusion, and you can check the diffusion parameter, and you can see that how spatiotemporally that drug release has a unique pattern. And you can control this pattern. So that is most important. And the later phase, we check this one for their using an antibiotics and checking how these antibiotics are killing that corresponding microbes. Now this kind of systems we tested for this osteogenic properties. In the case of osteogenic properties, we check couple of parameters. So here first one is the alkaline phosphatase. So then you can see this, the blue one is the implant or the scaffold, that is a quite high. We take two controls. One is the simple TCP, which is a two-dimensional control. Another one is an hydrogel, which is not a bead system, but a normal hydrogel. And we make this one. And then we check some of the expressions of osteogenic markers like RAMS2, collagen, and we found a good increase of these markers and then their relative expression. Then we check their corresponding cytoskeletal organizations and this biomineralization over days of 14. And finally, we implanted this stuff in vivo in murine system, and we see that over a period of time when you are using this kind of system, not a normal gel, so there is a very clear and evident formation of the blood vessels. So with this evidence, we got an idea that these two kind of approach that we are adopting has a good potential to be used as an say for this purpose of engineering the angiogenesis for an effective tissue engineering. So these are my collaborators, and a few of my friends are from, say, NIT, Professor Kunal Pal, Professor S. Giri, who actively participated, and Professor Salem, who was earlier in NIT Rourkela, now have moved to in Bhubaneswar. So I just forgot the name of the institute. And these are the students who contributed in that particular, all these 3 different works. With this, I would like to thank you all for the patience listening, and I'll be happy to answer questions.
Any questions?
Sir, you mentioned like a hexagonal structure. Why to use the type of structure instead of, like, there are different types of structure out there, but why we need to use the type of octagonal or hexagonal structure?
No, what we did, it is not hexagonal structure. What we did is we followed the hexagonal close packing format. Beads are spherical. So if you look into this, beads are not hexagonal, beads are spherical. But when we organize the beads, we organize this pattern. Please let me zoom it. Then I hope I can show you this. So this is the unit. Please see, this is the unit. We organize the stuffs in this format. This unit is hexagonal close packing. The moment we are doing these things, this hexagonal close packing, then our stuff is become, say, we are getting, our objective was to get and defined microarchitecture without doing micro manipulation. So the stuff is technically a bigger one, macro system. We don't need any micro level technique. But using this one, we are being able to generate a structure which is micro. That was our objective.
That is fine.
Fine, sir. Fine. Thank you, sir.
Any further question?
Thank you too much, Dr. Banerjee. It was very nice to hear you back. So my question is...
yes, same. First of all.
So my question is, so mostly what happened when you implant some, foreign material in the body, like body actually tried to, cause some inflammation. Those material cause some inflammation reaction.
Yeah.
They try to, cover some kind of fiber tissue on those material.
Exactly.
So did you see any observation, or like because you are using some, angiogenic biomaterials, so that alleviated that problem?
Yeah, no, but we did that ectopic, say, transplantation. We did not notice such inflammatory response. One very important point I would like to mention here also. So we check this one, say, after 14 days. So by 14 days, even in the inflammatory response, it is very obvious that there could be a little bit of inflammatory response. There is no doubt that. But as we have not, say, took out that implants at the day 3 or day 5, it is difficult to tell whether in that period there was an inflammation or not. But later phase we did not observe. And even when we checked the histology, we did not find that major involvement of the neutrophils at that site.
Okay, thank you.
Any more questions? I guess we don't have any more questions. Thank you so much, sir, for your time today. It's a pleasure having you here with us once again and being able to witness your presentation today. Thank you so much, sir.
Yeah, pleasure. I'm also very happy to be a part of this one. And on my behalf, I would like to thank the organizer once again. Thank you.
Thank you, sir. We now move on to the last presentation of the session. And I'd like to invite Dr. Srirup Banerjee to speak on understanding gastrointestinal biomechanics, role of medical image processing. Dr. Srirup Banerjee is currently serving as Associate Professor in the Department of Mechanical Engineering, Haldia Institute of Technology, Haldia, West Bengal. He has 6+ years of experience in academics and research experience in the field of biomedical engineering. His research area of interest is biomechanics and medical image processing. He has done bachelor's degree in mechanical engineering in 2004 and master's degree in biomedical engineering in 2006. He has obtained his PhD from Department of Biological Sciences and Bioengineering, IIT Kanpur in 2014. He has served in the Department of Bioengineering in NIT Agartala and VIT Bhopal University respectively in various capacities before joining HIT Haldia. I now request Sir to begin with the presentation. Over to you, sir.
Okay, thank you for the nice introduction, and I'm really honored for selecting me for a presentation in this conference. I'd like to thank the organizers first. So in this difficult days, new normal, this is a new experience for me. So we're presenting from at a distance. So I like to ensure that my voice is audible. Is it audible?
Yes, sir.
Okay, thank you. So let me first share the screen. So is it visible?
Yes, sir.
Okay, thank you. Okay, let's begin with the talk. So you can see the title of the talk, that is Understanding Gastrointestinal Biomechanics, Role of Medical Image Processing. So by looking at the title, you can understand that the talk is going to be something to deal with gastrointestinal tract. Now, why somebody will be interested in gastrointestinal tract? Because he or she wants to understand the functions of gastrointestinal tract and the mechanisms by which that function is accomplished. Now, why somebody will be interested in that is because if something goes wrong in gastrointestinal tract, the information, the understanding of from those researches will help diagnose and treat those disorders. Now, the next term here after gastrointestinal is biomechanics. So you understand that the functioning of the organs of gastrointestinal tract is basically largely dependent on mechanics. The role of mechanics plays a considerable part here. In the second part, there is the medical image processing. So this is basically one of the ways to assess different kinds of physiological phenomenon that is taking place in gastrointestinal tract. So my talk is divided in two parts. The first, we will elaborate on this gastrointestinal biomechanics. To be specific, I will limit my discussion to that of the stomach. And next, we will see how medical image processing plays a role in understanding them. Let us begin with a simplistic diagram that we are familiar with. So this is our digestive tract. We know from our school days that it is a long and dirty tract that starts in the mouth, from where we engulf food. We chew the food to form bolus, which is transported through the esophagus right down to stomach. In stomach, the food is further churned down into smaller pieces and mixed with digestive juices, and ultimately the nutrients gets absorbed in small intestine, and the portion which cannot be absorbed is thrown away through the means of anus in the form of feces. Now, stomach, our focus area of this talk, is situated right in between esophagus and small intestine. So it is connected proximally to the esophagus, where esophagus joins in the medial region of the stomach, and there is a tight group of muscles called lower esophageal sphincter that remains closed. Usually, unless and otherwise there are some physiological cues. And at the other end also, in the distal end also, there are another tight group of muscles that is called pyloric sphincter that also remains closed unless and otherwise there are definite physiological cues. Now, if you look here, the stomach can be largely divided into three regions. The dome-shaped region over here, just besides where the esophagus enters here, is called fundus. Then there is a passage which is called body or corpus, and then the corpus connects fundus with that of the distal part of the stomach, and from where the stomach there is a sharp vein in the stomach. Now, the stomach is a hollow organ. So it is much like you can consider as a balloon, but unlike balloon, the walls of the stomach has several layers. As we can see here, the outermost layer is serosa, that is a connective tissue layer. Inside there are different muscles. There are three different muscle layers. The outermost one is longitudinal muscle layer. The outermost one is longitudinal muscle layer, which are oriented in this direction, along the longitudinal direction of the stomach. The next one is circular muscle layer, and the innermost one is oblique muscle layer. So the oblique muscle layer is not covering the whole part. Beneath that, there are submucosa and mucosa. So in submucosa, different blood vessels are supplied, and in mucosa, as you can see here, different gastric glands are there. So this is a briefing about the anatomy of the stomach. Now let us look what are the functions, major functions of the stomach. There are three major functions of the stomach. The first one is storage. We have food, and at one go we have a considerable amount of food, and that food needs to be stored somewhere. Stomach provides that storage space, which is called the formal name of it, the physiological phenomena is called gastric accommodation. Then, even though we chew our food and break it down to smaller particles, it is not sufficient. We need further grinding of those particles into smaller pieces and mixing it adequately with digestive juices. And that is also another function of the stomach. Lastly, there are controlled release from stomach to small intestine such that the small intestine can adequately absorb the nutrients. So that is gastric emptying. So in this talk, we will primarily focus on gastric accommodation and gastric emptying. Before beginning to discuss their physiological phenomena, as we have said, the mechanics plays an important role. So let us have a look at the stomach from a simplistic model, mechanical model. So let us consider the stomach as a pressure vessel, just like here. We have shown a cross-sectional view of it, where there are stresses. The gastric wall stresses will be there. If there is food content inside, there will be some internal pressure, there will be external pressure. We can connect these variables in a Newton's law-based force balance in this fashion, where the internal pressure and the stress on the gastric wall, understandably, they are linked. So as the internal pressure will increase, so in this case, in the case of stomach, intragastric pressure increases, the gastric wall stress is supposed to increase. So that means whenever we eat some food, the intragastric content will increase. If the intragastric content increases, then intragastric pressure is supposed to increase, and then immediately the stress will also rise, and we should feel some discomfort. Okay, but here, even though I have earlier said that stomach is like a balloon, there is a deviation. The stomach, in certain cases, has some other ways to tackle these issues. Unlike when it is seen, when the intragastric pressure is plotted with gastric distension, it is seen that unlike balloon, the pressure-volume relationship of stomach is not linear. So stomach finds its way to tackle this problem, that whenever we eat some food, we should not feel the discomfort. Obviously, there is a limit. If we just overeat, then at some point of time, definitely we are going to face the discomfort. That is also for our benefit. Okay, so let us try to understand the physiology of gastric accommodation. So here is a schematic of the proximal stomach, where we can see the fundus region of the stomach, the lower esophageal sphincter, where esophagus is entering into the stomach. This black line is the pressure profile along the lumen. We see that as the lower esophageal sphincter is closed here, there is a sharp peak here. So this is a high pressure barrier, and this high pressure barrier is needed, because otherwise, if you see the pressure profile, this is the pressure inside the stomach is higher as compared to that of the esophagus. So if you remove this high pressure barrier, then what will happen? The highly acidic content of the stomach will flow back to the esophagus due to this pressure gradient. And our esophageal wall is not at all prepared for handling those acidic contents. So, I mean, if accidentally these things happen, then we feel the heartburn. So, but naturally, this should not happen. So, when food is about to come, then there is a neurohormonal input, and that neurohormonal input causes some interesting phenomena. What it does, it relaxes the muscles of the proximal stomach. There is the fundus. So it just alters its mechanical property such that it becomes a relatively softer material. So it reduces the stiffness. So now you can understand, again, I will draw the comparison with the balloon. In a balloon, if certain portion becomes weaker material, which is less stiff, then what will happen? That portion will protrude. The similar thing happens in our body when we suffer from the painful condition of hernia. What happens is that in some internal organ, if some portion of it becomes weaker, then the internal pressure may cause a bulging of it, and that bulging may hit some other organ to cause pain. So the similar mechanism here, the deliberate neurohormonal input from intestine as well as from the stomach causes the alteration of mechanical property of the fundus. As a result, there is a decrease in the gastric pressure as compared to esophageal pressure. Now, the gradient is favorable, so that if the food bolus comes here, it can, due to this pressure gradient, can come inside the gastric lumen. So, in short, the gastric accommodation helps food to enter the stomach. It provides a storage space for stomach for the food, and also importantly, it allows ingestion without significant intragastric pressure rise. Now, once it is stored over here, then this food can be broken down into smaller pieces, and once it is broken down into smaller pieces, then it will be emptied in a controlled manner. So we had kind of briefing about the gastric accommodation. So let's find what happens in gastric emptying. In gastric emptying, again, the neurohormonal control plays a role. So it is triggered by different kinds of meal properties. So when the stomach is in empty state, then what happens is that some portion, some of the milk readily go to the intestine, and the sensors in the receptors in the intestine, they sense the nutritional value of it. They send a feedback through neural route, through hormonal route as well, to the stomach, so that to control the gastric emptying. Now, in the initial phase, when the gastric accommodation is needed, the muscle relaxes. Now here what happens, then the gastric muscle, mainly proximal muscle, stiffens, and there is a global squeeze of fundus. And this squeeze of fundus raises the intragastric pressure over here, and if we focus our focus in this small area near the pylorus, we see that the antral pressure here, as a result, increases. If the antral pressure is increased and the pylorus is open, the pylorus is not open always, so it is intermittently open. When the antral pressure is high and pylorus is opened, then the gastric content can be delivered to small intestine for absorption over there. So now we have also observed that in the earlier studies that there are specific patterns of solid and liquid empty. Okay, now in liquid, from the time it is ingested into the stomach, from then onwards its gradually it just starts empty. But for solid, it needs some time. So initial half an hour is needed. That lag period is there. So at that time there is no emptying, and after that there is a linear empty. So typically our food is a mixture of solid and liquid. So it's safe to say that when you eat the food, the liquid portion starts emptying. The solid portion is stored in the fundus. As per the current notion, it is stored somewhere in the stomach, and it is breaking down into smaller pieces, so smaller particles, and then it just starts emptying. So we understand that mechanics plays an important role in the gastric physiology. So the major contractile patterns of the muscles that are responsible for this. What are the different the contractile patterns? Fundic relaxation over here, which helps in food storage. Fundic contraction, which is the dominant player in the gastric emptying. And these are tonic contractions. So these are not phasic contractions. It does not occur in phases. It's a sustained contraction or sustained relaxation. But here there are some phasic contractions that is called peristalsis. So peristalsis in esophagus or in small intestine, they help propelling the food. Here the role of peristalsis is different. Peristalsis, along with segmental contraction and along with pyloric opening and closing, helps churning those foods into smaller particles. It helps in mixing and grinding. So when visualize the condition when the pyloric end is open and this kind of contraction moves here, so a small chamber is created over here. In this small chamber, due to high shear force, the food particles break down into smaller particles, and there are considerable mixing. As we have said, the mechanics plays an important role, so it is important to understand the mechanical properties of the gastric wall, and people tried that. So earlier, it's difficult to analyze mechanically the human stomach, but earlier people tried with the cadaver stomach. But in early 2000, a group in Aalborg Hospital in Denmark, they have done a series of experiments. So one such experiment I'm just demonstrating. So they have taken a pig stomach fresh from slaughterhouse. They brought it to the laboratory condition, and they have analyzed them. What they have found is that when they have measured the thicknesses of different layers of stomach, they are different. So if you just the intact stomach wall, it is thinner in the fundus, relatively thicker in corpus and antrum. Muscle is again thinner in the fundus, gradually thickens as you move towards the antrum. Mucosa submucosal layer is thickest in the corpus region. So we have earlier mentioned this approximate relationship to understand our the different players in this mechanics. So we have said that the intragastric pressure plays an important role. So here we see the thickness also varies. Okay, so not only intragastric pressure, but also the thickness also definitely plays a role, and here the thickness varies spatially to alter the stress pattern. Now they went on to further analyze them. So here let us take cue from this schematic diagram. So here there are two materials. So one material is relatively steeper slope, the other material is relatively less steeper. So the steeper the slope, you can consider the stiffer the material. So with this knowledge, we can analyze this. So here it is. This is the properties of fundus, mechanical properties of fundus. These are the mechanical properties of corpus or body, and these are the distal part, that is the antrum. Now the interesting thing we see is that in fundus, corpus and antrum, the mechanical properties differ. The mechanical properties also differ depending on different layers, muscle layers, and we also observe that the mucosa submucosa layer, it has a relatively higher mechanical property as compared to that of the muscle layer. So I mean possibly the mucosa submucosa layer provides a baseline level of mechanical strength to the stomach wall. The muscle properties play a crucial role in serving those physiological phenomena. So in a nutshell, from this graph we can say there are spatial variations of mechanical properties. So the gastric wall properties are inhomogeneous. Not only that, if we see other plots in the study, we can see that this is for fundus, this is for antrum, this is for corpus, this is for fundus. And here, this is the circular muscle and this is the longitudinal muscle. So that means not only in different region those mechanical properties are different, but also in the same region, if the directionality is different for different muscle layer, they are different. So not only the gastric mechanical properties are inhomogeneous, they are anisotropic as well. Now, so far they have done, so they have conducted several experiments to understand the mechanical property, even though it is not for human stomach but for pig stomach. But that is not a full picture because those are biological tissues. They have, what they have analyzed when they are chopping off certain portion of it and analyzing, what they are analyzing is the elasticity, that is the passive property. Now, there is an active component of it which is triggered by those neurohormonal inputs. And interestingly, the earlier notion was that there was only neurogenic input there, that is stimulation by nerve that alters some certain mechanical properties. It was later observed that with the discovery of interstitial cells of Cajal, and there was a growing understanding that interstitial cells of Cajal ICC plays a role over there in those gastric contractilities. Okay, so it is seen that in some cases where the contractility is hampered, there are some irregular pattern of this in the absence of interstitial cells of Cajal. So there is a myogenic, that is from within the muscle, there are some controlling controlling zone that also changes the mechanical property. So in a nutshell, there are different players in these gastric events of accommodation and emptying. So these are different players and they are interrelated. So if you ingest food, intragastric pressure will increase, that will cause gastric tension increase, that will cause the gastric stress wall stress to increase. Similarly, the same intragastric pressure will cause a change in gastric geometry as well as increase in intragastric volume. Now, these two will contribute to gastric wall strain, and the stress and strain, they are related by constitutive relation. So from there the mechanical property comes, and the mechanical property is again inhomogeneous, that is direction dependent, that is anisotropic, and there are active and passive components of it. Now, the upstream of it, why the mechanical property alters and how those propagations are there. So there are also electrophysiological studies, that is the gastric wall membrane potential plays a role, so it also contributes in this whole scenario. So if we have to understand the physiological events, we have to understand all of them and their interplay. Now, if those interplays go wrong, then there can be gastric disorders of accommodation and emptying. So here I have enlisted 3 such disorders. First is functional dyspepsia. So the dyspepsia name is pretty common. Okay, so but the term functional here means that there is no physical obstruction. So whatever obstruction is there, that is due to some disorder in the functionality, and definitely it causes some early satiety and fullness, and there is a chronic pain over there. Then there are rapid gastric emptying. So first of all, if you cause the gastric emptying too fast, intestine will not be able to cope, and intestine will not be efficiently absorbing the nutrient. Moreover, there are some associated physical discomforts like nausea, vomiting, bloating, cramping, diarrhea, etc. Last but not the least, there is another disease called gastroparesis. So it literally means stomach paralysis, which is nothing but a delayed gastric emptying. So you get the condition that you are eating some food and the food is not emptying from the stomach. That is possibly because the contractile patterns are not working properly, and then it happens that you eat a small amount of food and you suddenly feel very full. Not only full, you experience nausea, he experience some epigastric pain and tend to vomit. Okay, so as a result, what happens is that a person who is suffering from gastroparesis, he fears eating food. So after suddenly eating some small amount of food, he feels these discomforts. So then his eating pattern gets in completely disarray, and he suffers from malnutrition and weight loss, and his personal and professional life is in disarray. And further complications are there that if the food stays for a longer duration there in the stomach, then what will happen? The acidic environment, the acidic environment the acid secretion will stop, and there will be a fermentation of food. Also, the food can harden to cause further other complications. Importantly, gastroparesis is often associated with diabetes. So diabetic patients which are suffering for a longer period of time, it is seen that they also develop gastroparesis. Now, India is called the diabetic capital of the world. There are growing cases of diabetes over here, and definitely the older patients, the patients who are suffering for a longer duration of time, they will suffer from gastroparesis as well. So that causes the blood glucose management more difficult. Now, to cure them, then we have to investigate the problem. So how to investigate the problem? There are routes of animal study as well as human study. So in animal study, you have, in both the cases, normal and disease, you can do experiment on. In vitro experiment is possible for animal. For human, it is not possible except for cadaver studies. But in vivo experiment gives you more detail, because you can assess the physiological procedure as it happens. And in some cases, if you can take cues from those in vivo, certain in vivo experiment, you can perform computational study as well, and medical imaging plays an important role over here. Now, the different measurements, so we understand that now this gastric events are multifaceted events, so there are so many parameters, they are playing with each other. So what are the different measurements of gastric events? Intragastric pressure is the first one. So how to measure it? So you have to insert and probe inside the stomach to measure it. Gastric wall geometry, you can get an understanding non-invasively by means of different kinds of imaging. Obviously, those imaging has their own advantages and limitations. Gastric wall tension or gastric wall stress, you can put some strain gauge and you can some indirect measure, you can set to get a value of it, but again, this is not possible. Every time that a person is ill, you just open his stomach and put some strain, mount on strain gauge over there. It's not possible. In some animal study, it has been done. Gastric wall membrane potential, electrogastrography is the option, but again, there is a problem of non-specificity. You cannot locate them from which spatial orientation is happening, and there are also some problems of noise there, so you have to filter them out. And intragastric volume, there are different techniques that are done. So like barium swallow X-ray, that you basically the main procedure is that you prepare some meal with some agent, contrasting agent, or with some radioisotope. You give it there and you image. So in barium swallow study, you use X-ray to see that with how much time the gastric content is emptied considerably into small intestine. In gamma scintigraphy, you put some radio isotopes over there. So some those are sensed then. In barostat, it's an invasive technique. You put a plastic bag inside the stomach, okay, and you maintain when the stomach is contracting, you take out some air from there by means of some electronic relay, and when the stomach is expanding, you infuse some air, and as a result, you maintain a constant volume. So it's kind of an indirect amount of measure to find out the relation between the pressure and volume. Last option is definitely imaging, and it's a non-invasive technique. So now there are several types of imaging, but every imaging has their own advantages and limitations. Like the main problem in imaging is that for gastric studies is that they are relatively slow process. If they are relatively slow process, then what happens is you expose them, say you are using X-ray or CT scan, you are exposing them to ionizing radiation for too much time. So magnetic resonance imaging is an imaging technique that is free from ionizing radiation, that also gives a better contrast for soft tissues, which is needed for this kind of gastric imaging. So, but again, I mean, there are limitations of magnetic resonance imaging as well. So, first of all, this is relatively costly. Secondly, is that there are some patients with some metal implants, they cannot undergo magnetic resonance imaging, and obviously the main problem of magnetic resonance imaging, so that it is now limited to certain specialized research groups, is what we will discuss. Okay, so now you get those images. Now what to do with these images? So you have to you want to know that how much volume change is there, so you have to reconstruct the 3D. And even though you see in your textbook this kind of pretty picture of stomach, the actual stomach may be like this. So this is reconstructed from MRI images. So where the lower esophagus enters somewhere here, and from here the small intestine goes from pylorus. This is the fundus, this is the antrum, this is the corpus luteum. So this is 3D reconstructed geometry just after meal infusion in the stomach. After 1 hour after meal infusion, its configuration can change drastically. Okay, now how to achieve these 3D reconstructed geometry is that there are MRI images are typically like this. So this is a representative image. It's a sagittal image. That is along a plane which divides our body into left and right section. So readily you can see this is a kind of medial sagittal image. You can see the spine over here, heart over here, and this portion is this highlighted portion. This brighter portion is stomach. This is brighter because some contrast agent named gadolinium is mixed with a nutrient liquid. This small portion is liver. So now we have a series of this kind of images. So from this image, to construct this, we need the techniques which are called medical image processing. So I will give a glimpse of how much challenging it is that this is a protocol that I have used to assess some of the gastric events from the data obtained from University Hospital Zurich. So here they have studied 16 healthy subjects in a series of MRI scans and concurrent pressure measurement by inserting a small pressure probe over there. So what they have done is for each of 100 ml of meal infusion, before the meal infusion and after each 100 ml of meal infusion, they have taken one MRI scan for the entire stomach, and after meal infusion till the next 1 hour, they have taken several at every minute they have taken one scans. Okay, and each scan comprised around 13 seconds. So there are different meal volumes they have used. So 16 healthy subjects and 3 studies each. So these are one of the representative scan you can see. So these are the scans basically. If you look at it, these planes has been scanned. So here it is. The head of the patient, the subject is somewhere here. You can see over here. This is the heart. This bright portion is stomach. Then there is a black portion. The black portion is air. Here, this is the black portion is air. The bright portion here. This is the stomach. So we have to identify them. Now each such scan comprised of 40 images spanning the entire abdominal cavity. Okay. So the challenge is if we have to form this 3D image from this. We have to identify the regions of interest, and in this particular, I will give example from this particular study. There are 16 subjects, 3 studies, so total 48 studies. In each study, as per the protocol, there are 63 to 69 volume scans. So total, if you consider an average of 66 studies, then there are more than 3,000 volume scans. Each scan, we have said, there are 40 image slices. So it totals more than 1 lakh image slices. So if you have to make in the conventional image processing softwares, you have to go at every slice and you have to click at least once. So if you have to click at least once, then you have to perform more than 1 lakh clicks to complete the overall procedure, and this is time taking and tedious. So an efficient way for 3D reconstruction is needed. Otherwise, this is hindering the application of MRI or any imaging strategy to harness its potentiality potential in its full. So an image processing platform is developed to tackle this challenge. So here is a glimpse of the graphical user interface where you can load the image. You can use different kinds of tools to identify these regions. This is made in such a way that you don't need to manually identify edges in every location, but rather you can take 3 to 4 judiciously chosen MRI scans along arbitrary orientation, and finally from there you can do this 3D reconstruction. The typical segmentation techniques used is thresholding, where you are clicking here and based on image intensity you are selecting, or it can be research that you are clicking at 2 points and you based on those points you are generating those foci and you are sending some rays which are finding the edges along the highest contrast along these vectors, or any other sophisticated techniques like live wire or active contour and so on that can be used for this kind of image processing. Now, once you get the points all over the images, now the problem is the images, the points you get around the RY, those points may not be properly connected. So there is an algorithm we have developed that is called magnetic linking, which identifies and sorts these orders. So here it is. This is an arbitrary shape, and here you have ordered all the points, and then what you have to do, you have to join them. Once you join them, then you get those contours and you form a contour stack. So once you form the contour stack, then all you have to do is to fit a surface over there. So here the specific function has been selected. That function has a value of 0 on the object, so that's how the 3D reconstruction has been created. But in this method may sometimes not work efficiently for intestine. So this is a kind of coronal image for small intestine, and here you can see the stomach. So these fragmented ROIs that may cause problem. So in that case, we have developed another method that we will use the thresholding approach in 3D. So you click once, and definitely there will be some further adjustments. So we can form the whole intestine. We have formed also the stomach. Stomach is relatively easier. So once we have developed the image processing platform, so we can generate a lot of data. Now those data can now be used for post-processing for further assessment of different kinds of problems. So, and those assessments, those post-processings will be custom made. For each problem, you design your own method of image processing and post-processing to tackle the problem. So here is one problem that I like to discuss, that the regional contributions of in gastric physiology, that is this fundus, body, antrum. Previous studies indicated that there were different roles of it, but there is no measurement of it, because it is difficult to extract those data for a large number of patients and for a large number of subjects and measure the volume actually. So with this image processing platform that has been made possible, it is also observed that if you surgically chop off some portion of the stomach, then the gastric emptying pattern they vary. Emptying and accommodation, both of them, they change. So from this, there is a hint that the different regions of stomach contribute differently to these gastric physiological procedures. So to do that, we need to compartmentalize the stomach into different regions, but there is no standard basis of compartmentalization. Okay, these are not very well defined. So what we have done is we have chosen a gastric axis, to be precise, gastric longitudinal axis. But how we will determine that? We have a series of contours. In each contour, we have identified the furthest point from these points. Okay, this is the furthest from all these points. which is Euclidean distance transform. So we get a series of points for all such planes. Once we get it, we fit a plane to all these points, and that will approximately run along the median direction of the stomach. So in that plane, we get the stomach contour. We get the stomach contour, then we apply. So this is an initial idea about where the gastric axis can be located. Now we take the EDT, again Euclidean distance transform, and take double derivative of it. Once you take that, we get a nice and fine ridge over here. Now our task is to identify this ridge. Once we identify this ridge, we get our next estimate of the gastric axis. Now it is in the medial region, but it is in single plane. The third, what we do is we apply active contour algorithm. So it is something like that, as if the stomach wall is repelling this particular curve. So this curve will then twist and turn a bit, and ultimately after several iterations it will stabilize. So that is our final gastric axis curve that connects the two openings of the, and here the pyloric opening and here the lower esophageal sphincter opening. There is the gastric axis curve. Now there is this anatomical measurement, anatomical landmark, that is incisura on gastric axis. Based on that, we have derived two base fitted lines. One is for distal region, one is for proximal region. Based on this, we have divided the stomach into 7 volume segments. Approximately V1, V2, V3 corresponds to fundus. V4, V5, V6 corresponds to corpus. This portion is the antrum. Now once we get these volume segments, we can measure the volume. And some interesting phenomena we have observed is that when we plotted them, so this is the volume of different segments, and per infusion volume for per 100 ml volume, the initially meal goes to distal stomach, as opposed to the common notion that meal gets stored in the proximal stomach. Initial meal gets stored in distal stomach, then proximal stomach reservoir starts picking up its volume, so then the meal stores in the proximal stomach, and the mid stomach acts as a conduit. Now in the post-filling phase also we have got certain interesting results. So here is the V1, that is the proximal most segment, shows a distinctive pattern. So there is initial increase in volume, then there is a plateau phase for near about 30 minutes, and then there is a steady decrease in volume. So it indicates that the once it is a bit delayed, and once it is this proximal stomach takes over the accommodation, then the majority of the accommodation takes place in this region. In the rest of the regions, we see there is no such plateau phase. Okay, so now we have done further analysis. So here I am presenting a qualitative analysis of gastric filling. So as we fill the stomach, this is the 3D reconstruction diaphragm from the MRI images, and these are different stomachs from darker to brighter. As the filling takes place, the volume, the stomach shape changes. The first thing we observe is that the superior movement of fundus, even though there is certain superior movement, but it is largely restricted as compared to the distal part by the diaphragm. So there is a circumferential expansion of the stomach, and there is a longitudinal stretching of the distal stomach. The reverse we have observed when emptying takes place. Again, these are the different time points of emptying. The brighter is when the more food is there in the stomach. As the food is emptied, we have plotted them. We have made these images in such a manner that they are represented in a darker fashion. So this is the qualitative way of looking at it. Now we thought that can we have some quantitative measurement. The problem with quantitative measurement is that for that we need certain points, and we have to mark those points. We need certain landmarks. So we have identified 4 anatomical landmarks, gastric landmarks here. One is this top of the fundus, which is spondyc crest, lower esophageal sphincter, incisura on gastric axis, and pylorus. Now we have observed how these points are varying. What we have seen that with the intake of food, there is superior movement of the spondyc crest, inferior movement of the incisura, superior movement of the pylorus. So in effect, there is a stretching of the stomach in the longitudinal direction, and it indicates that there is a possible involvement of the gastric longitudinal muscles during accommodation. Now we have also observed the initial position of the pylorus is supero-anterior medial to incisura. But as the gastric filling takes place, as more and more meal is infused, the pylorus moves posteriorly in the early phase, incisura moves anteriorly then in the early phase, and then it reverts back. So it gives a hint that there is a torsion near this region, that is near incisura. So for whatever discussion of this gastric landmarks we have done, we have measured them in three standard anatomical directions like anterior posterior or medial lateral or superior inferior. But it may happen that the trend of the gastric movement is in some different direction. So we have done a principal component analysis to find out that there are different points over here. What are the principal directions of movement? So what we have found, an interesting point again, we have found, that corresponds with our previous observation of torsion is that when we are measuring the angle of the principal direction, the first principal direction of say these proximal two segments, they are not much. But when we are seeing that for the between the proximal and distal, we see there are a significant change in its the significant rise in this angle. So that means, again, the hint of torsion, that is also from this study also we can find a hint of torsion, but the major direction of the movement of the four gastric landmarks are not in standard anatomical planes. So to summarize, what we have found is initial storage of food is majorly in the distal stomach, and after 100 ml infusion, proximal stomach takes over. Okay, the mid-stomach region appears to be a conduit. The proximal most volume segment remains expanded for nearly 30 minutes. And from gastric landmark movement, we have seen that there is longitudinal expansion of the distal stomach as compared to the proximal stomach. The superior movements are restricted by diaphragm. Circumferential expansion is observed. Involvement of gastric longitudinal muscles in accommodation and emptying is observed, and there is a hint of torsion in the mid region. Now the question is, so we have seen that there are. This is a glimpse of what medical image processing can do, but whether this is all, clearly not. We are not able to unravel all the mysteries, all the relations, because this is a multifaceted problem. It is not possible just using one technique to do this, but computational techniques, which are, you can say, the downstream of this medical image processing, can take it forward. So we can have the numerical methods like finite element analysis. So where you are dividing once say you have generated the gastric regions, you are dividing into smaller regions of regular structure. So you are analyzing different constitutive relationships. Say you are understanding estimating the stress, strain, deformation at these nodes, and intermediate regions you are interpolating to find it. So this kind of methods can be used. So I will not go in depth, but I'll show some preliminary results. So here is one such finite element analysis of the gastric wall, putting appropriate constants. So these are the stresses that are observed. So the blue means low stress, red means high stress. So the maximum principal stress is shown here. This is the minimum principal stress. So now again, in this kind of analysis, there are problems. As we have said, the gastric, we have to ascertain, we have to, give the properties of the stomach wall. The properties of stomach wall are not, we have not estimated, in a very efficient manner till now. The passive properties we know are different regions. They are different. There are this anisotropy and inhomogeneity, but active property again, it's a you cannot ascertain fully. So those things are yet to be done. So far, these kind of studies are being done, but more and more information, more and more techniques have been generated. They will be more. They will yield better results, and you can use them as predictive tool. And in this in this analysis, we have shown only the wall, but the main content of the stomach is inside. Okay, so gastric content, how it empties there. So there is you have to do fluid dynamic simulation, and obviously as stomach wall is moving and exerting pressure on the fluid, and fluid is in turn exerting pressure on the stomach wall, the intragastric pressure. So there is two-way communication between them. There is fluid mechanical consideration, there is fluid-solid interaction, and those are a different ball game. So then there are another approach is that another unexplored area, relatively unexplored area, is electrophysiology studies, that why all this muscle movement is taking place, all these contractile patterns are taking place because of certain electrical activities. Those electrical activities are generated and they are translating them to mechanical activities. Those mechanical activities of gastric wall is then contributing to the fluid mechanical incidents that ultimately causes gastric emptying. So and this picture is from images are from the study of one Auckland-based group in New Zealand. They are studying them. So the primary data for electrophysiology, again, they are getting from EGG, and then there are some high resolution serosal electrodes are placed and some measurements are taken. So that gives a better spatial information about those electrical origins. And then in earlier stages, they use relatively simplistic geometry, as you can see here, with the improvements in this image processing technology. Now, gradually, the real stomach geometry can be used for analyzing this kind of data. Now, so the concluding remarks is that the medical image processing. So, if you see in this case, there can be some clinical implications, like in the study I have discussed. Larger volumes of meal should be used for scintigraphic test, because typically it is currently used 200 ml. So for 200 ml, 100 ml goes there in the distal region directly. So you want to know that whether the gastric accommodation is taking place in fundus properly or not, because the fundus is the main region where the gastric accommodation takes place. Then you can consider a relatively larger amount of test meal. And bariatric surgery also focused on the fundus. So now, if you chop off fundus, but the person who has eating disorder, he is taking a smaller amount of meal, then the frequency is large, then also it will be difficult to control the weight. Now, there can be, as we have discussed, there are further research avenues. That 3D gastric models provide a practical and non-invasive alternative to invasive barostat for measurement of gastric volume, and it provides a cue for downstream mechanical and electrical analysis. Now, we understand that medical imaging plays an important role in the assessment of physiology, not just gastric physiology. Here we have started our discussion. We have done all the discussion on the gastric phenomena, but for any physiology, medical imaging in a non-invasive way, and it gives kind of structural changes over there. Now, if you can come up with a functional interpretation of it from some other experimental technique, then things will be completely unraveled. And not only medical imaging may produce, say, as we have seen here, 1 lakh images. Now you have to process them. So intelligent medical image processing algorithms play a pivotal role in realizing the full potential of these imaging techniques. In fact, this medical image processing is developed so that we can visualize different anatomical structures and we can measure different anatomical measurements. I will give some example which is other than the gastric region. So it is a venture medtech startup which we have done. We have formed, and we have analyzed several kinds of data. So here, as for example, you can see here, this is a chunk of stomach. This is the coronal plane. This is a arbitrarily oriented slice. This is the proximal stomach where esophagus is entering. We are taking certain anatomical measurements over here to understand the phenomena. Here, this is a completely different domain. This is the, again, coronal segment of CT scan, and these are kidneys that has been reconstructed from there. This is the hip joint. So this is the femoral head, and this is the acetabulum cup, and this is placed as it is. Where this can be used, so this is also again generated from TS data from a CT scan. Where this can be used for surgical planning. This can be used for patient-specific implant design. This can also be used for some mock operation or for some teaching purpose in 3D printing. So here is the 3D printed part from this same modeling. Okay, so this is the method used was selective laser sintering. So these kind of parts can be quite handy in in different kind of hospitals and clinics and for researchers. So here I like to acknowledge for the knowledge I have gathered and the research I have done to the Department of Biological Science and Bioengineering, IIT Kanpur, and MHRD, Government of India. I would like to thank our collaborators, Professor Mark Fox and Professor Werner Switzer and their team in Zurich and Nottingham for providing the data and for providing different kinds of technical assistance. A special thanks to our lab members in IIT Kanpur. So we had some really good discussions and that opened up different kinds of avenues in this research. Last but not the least, the main person behind this all the work is my PhD guide. Unfortunately, he is no more. So this talk I like to tribute him for all the knowledge that he has passed on to his students. Thank you. If you have any questions, I'll be happy to answer.
Any questions?
Yes, sir. Banerjee, sir, I just have one small question.
Yeah.
Yeah, sir, you said some gastric landmarks, right? These gastric landmarks, have you identified it automatically or are you plotting it manually?
Gastric landmarks, we have identified them automatically. Yes, you can say, I will not say completely automatically, I will say semi-automatically. Okay, like for say just one instance, that is once you identify the gastric axis from here where the short bend is there, from where you can identify the this incisura on gastric axis. Okay, so once you identify that, all you have to do is to develop an algorithm that will get the maximum bend over there.
Okay. Sir, you are saying 1 lakh images, right, sir? Wow. Does it mean like MRI is having 1 lakh images, or do you mean to say the whole data set?
What I mean to say is for one subject, there is for one subject, for one study, there are 40 images to cover the whole stomach.
40 scans. Okay.
Yeah, okay. Scans, MRI scans. So 2D images, 40 2D images. Now, if you multiply that with the number of times we are taking the scans per subject per visit, it ultimately the total number of scans for the whole study, for a meaningful study, becomes more than 1 lakh. That's what I mean.
So here, I mean to say, how many subjects you have tested, sir, here in this case?
In this, the data set I have shown there were 16 subjects. Each subject went to the clinic for 3 times, and in 3 times each study consisted of, on an average, 66 scans. Each of those 66 scans contained 40 image slices.
Oh, 66 scans.
Yeah.
Okay.
So So before meal infusion there is 1 scan, and after each 100 ml meal infusion 1 scan, and after meal infusion stopped, every minute 1 scan for 1 hour.
Okay, sir. What was the platform you used? You have developed some algorithm, right?
Yeah.
Okay. This gastric axis you have extracted automatically, no, sir?
Yeah.
So how did you evaluate that point, like the maximum point you mentioned, that maximum point from the control?
That is the Euclidean distance transform. That is straightforward formula is there. So basically we have all the points inside the contour, and there are contour points. So for each of the points we have to find the maximum distant point. Now all of them, for all such contour points there will be one point which is most distant. Now for all those group of points, which point has the maximum distance, then that point is the farthest from all such contours. That was the kind of idea.
Okay, sir. Thank you.
And there was one question in the chat box.
Yes, sir.
Yes, it's a very good question. That in MRI scan, wherever there will be different body parts that will be giving bright contrast. No doubt about that. So the problem will be when we do not know the anatomy, and when just besides the stomach there is some brighter part that is that is joined with the stomach. Then it becomes really difficult to identify that. But what we are doing, we are judiciously choosing some of the scans. In those scans, we know the anatomy. We are there using those segmentation techniques we have mentioned. We are semi-automatically doing the initial segmentation, initial detection of the ROI. So that's where the manual input is. It is not completely automatic. If it is completely automatic, then obviously we have to teach computer, okay, this is water and this is the stomach. That is really tough job. Yeah, anything else?
Any more questions? I believe there is no more question for you, sir. Thank you so much, sir, for such an informative presentation.
Okay, thank you for giving me the opportunity. Okay.
Thank you, sir. There is a question in the chat box for Indranil, sir, if he is around. Indranil Banerjee, sir. Alright, I guess he's not around. So with this, we wind up the current session. I would like to thank the chairperson for this session, Professor Devendra Verma Sir, for being here with us today. We may now proceed for our